No, we have started. Good morning. So, I welcome you all for the last day first session. So, today we do not have much technical thing, but you have to write exam at the end, and then we will conclude with a proper validity session, okay, where we will distribute your certificates, and maybe I request you to speak something about the event as a feedback. Okay. So, let us start my presentation. Oh, this is yours. So, today I will be speaking about solar collector testing and quality control, because in last 4 days what you have got the information about its fundamental and its various applications, and not only for only hot water generation, for hot air generation, and then for electricity generation. Also you have learned many things on design perspectives, like how a pumping stations can be designed, how we can design a off grid system. Of course, and today you will learn about design of a grid connected PV system, which will be taught by Professor Christophe in the next session. So, here in this presentation, mostly what I have covered is about the testing procedure for a liquid flat plate collector and a solar air heater, and then also few things I have included about drying of agricultural products. So, let us see how we can move ahead. So, this is the outline what I have listed for this presentation. This need of testing, why this testing is required, and then how this testing is performed in liquid fat plate collector as well as solar air heater, and drying kinetics and drying calculations. So, this drying calculations section I have shifted to this tutorial part, then we will do the calculations, and then you also help me in involving in the process of doing the calculations. And then finally, some of the aspects of quality and standards of FPC components, because see, until and unless you have a proper quality control, you cannot actually tell the efficiency of the plant and then its quality. What I mean, like suppose if we do not have this kind of standards, then any of the manufacturers can manufacture, right. So, people will not be having any range of parameters to control the quality. So, what will be the transmissivity? So, that has to be standard. So, if the extinction coefficient is about 4, so of course, your thing will be very transparent, and your quality will be very good. So, someone has to certify. So, I have attended one very important meeting in MNRA, and that the meeting was exclusively on quality control on solar flat plate collectors, because see, we need the flat plate collectors in everywhere, because it is such a nice technology, because you just install the device on your rooftop and you will get the hot water. You do not have to turn on the system which consumes electricity for generation of hot water, right. So, in Bangalore, if you see, in most of the household they are having liquid flat plate collector, and then there was a blackout in Bangalore, and then that was happened in the morning, and people have done a lot of research and finally found that this is due to use of greasers for hot water generation. Okay. Then this government took this matter very seriously, and they said every household you must have a solar water heater. If you could not produce the certificate that you have a these installations, then you will be not getting a lot of things from the government. Okay. So, this is very interesting, that is why it is very, very important. So, now before I start that testing process, you already know the different applications. This again I am reiterating it, what are the primary applications of this liquid flat plate collector. It may be for generation of hot water to meet the demands in the indoor swimming pools. Okay. Then the water heating in domestic applications, then milk pasteurization is also very, very important, we need hot water. Then power generation, and of course, at low temperature power generation. Then drying, solar water heater for biogas. Okay. So, why I have written solar water heater for biogas? If you see, say let us consider this northeastern states of the country, and if we consider summer and then winter. Winter in our place, it goes temperature reported minimum is about 13 degrees Celsius, and there are some places like Arunachal or maybe in Meghalaya, it goes sub-zero sometimes. Okay. So, what happens, this microbes what is inside the biogas plant, which is responsible for generation of biogas, they could not sustain at that temperature. So, we need to maintain the temperature about 30-35. It works best when the temperature of the digester is about 35, which is called mesophilic temperature range. Okay. So, if this temperature goes down, we need some kind of auxiliary heating. Okay. So, from where we can heat it? Can we install a solar collector and then use a heat exchanger which can be installed at the digester, and then you heat exchange it, and then that the heat exchange that the heat transfer fluid can be circulated again, and this will maintain the temperature, so that these microbes cannot die out, and they could not suffer in thermal stress. Okay. So, that is how I wrote this solar water heater could be used for biogas generation or maximization of biogas production rate. And slurry drying. So, biogas plant, you have inlet tank, and then you have fermentation chamber, and then outlet tank. So, from the outlet tank you can take the slurry out, and you can apply in the paddy field or maybe in the vegetable gardens or maybe in the flower gardens, right. It is very good nutrients level. So, can we make some kind of dried cake which can be sellable, and for that condition we can use this drying, solar drying. Okay. So, these are just some of the additional applications of liquid flat plate collector, and what I am showing here, how we can maintain the temperature in swimming pool. So, we have collectors, it is arrays, not only single collector, there are many collectors which are connected in series or parallel, and then you need pumping systems, then filters, and then you regulate the amount of water required to heat exchange to maintain that particular temperature needed for swimming pool, right. Also, you have seen the use of FPC for power generation, right. So, what you can see here, it is a solar flat plate collector, it is arrays of solar flat plate collector, and you raise the temperature, and I am saying a simple liquid flat plate collector which can deliver a temperature at 100 degrees Celsius, right. Then your storage is at 100 degrees, maybe 100 degrees Celsius, and you can use the intermediate fluid or maybe the other fluid like organic fluid, which can be bring back to this liquid part, which is nothing but storage, and then exchange the heat. Okay. And you identify a fluid which will evaporate at low temperature like ammonia or other refrigerant. Okay. Then what happens, that can be expanded in the turbine, and then you condense it and then use a pump to circulate. So, we have three different fluids. In the first case we have maybe glycol or maybe water, or maybe in between you can have another secondary fluid, and then you will have tertiary fluid, or we can actually reduce this secondary part. So, we can have only two fluids if we remove these purple colored lines or heat exchanger, right. So, here it is very easy to find out the Carnot cycle efficiency, right. it is eta Carnot is something like 1 minus T2 by T1, right. So, T2 is what is your outlet and T1 is the inlet temperature. So, you can find out. So, if you do these calculations, the efficiency of this kind of system is very, very low. So, as you go on increase the inlet fluid temperature to the turbine, then what happens, you can maximize the Carnot cycle efficiency. So, that is how we are getting very low Carnot cycle efficiency here. Okay. But what you need to do for this kind of management, you need to have different kind of working fluid. Okay. It is an organic fluid. So, it may be R11, R113 or maybe R114 or that kind of fluid having lower boiling point. Now, why this standards testing is required is of course, the for comparing the efficiency of different types of collectors, okay, and an essential basis for their selection for a given application as well as their design improvement. Okay. So, once we set up this testing rig, then we can say okay, these are the parameters which influences the performance of the flat plate collector. So, what could be the design perspective? Can we increase or decrease the transmissivity? Can we increase or decrease the inlet fluid temperature? Can we increase or decrease the mass flow rate, and what mass flow rate it will work? But in case of liquid flat plate collector, since the liquid side heat transfer coefficient is more, then we do not have to perform the experiment at different mass flow rates. So, single mass flow rates will give you the entire characteristics of the collector system. Okay. But in case of solar air heater, since it is air, its heat transfer coefficient is very, very low, then we need to perform the experiments at different mass flow rates. Okay. So, what are the essential requirements for this testing? We need an arrangement for inlet fluid at constant temperature with flexibility to set different values of inlet temperature. So, so that we can control the temperatures, and we can see what will happen if we change the temperature inlet. Okay. And then pyronometer we need to measure this watt per meter square or what is called global radiation and diffuse radiation. Then provision for recording mass flow rate and different temperatures. That means we need mass flow meter and thermocouples, thermocouples. So, we can that means it is a temperature sensor. So, we call it as temperature sensor, and equipment for measuring pressure and pressure drop across the flat plate collector. Now, if you see, this is the arrangement we normally do for outdoor flat plate collector testing. So, what you could see that the first part, this is the flat plate collector what you have purchased for testing, and then we have flow meters, we have pumps, then bypass valve. I will explain the function of each and every component used for this testing purposes. And this red colored rectangle is quite interesting. We need cooling water and heat exchanger and then storage tank, and sometimes if we could not provide the sufficient temperatures, we need an electrical heater. So, this component actually very, very important, as mentioned here. This controls the fluid inlet temperature and fluid flow. Okay. So, that is how the combination of heat exchanger and the storage tank with an electric heater provides a means of for adjusting and controlling the inlet fluid temperature to the collector to a desired values, right. Here what happens, we need to perform the experiment at desired temperature and mass flow rate. Okay. That is how the function of bypass valve. So, here what happens, if we have to perform at certain mass flow rate, say maybe M1 kg per hour, that is a mass flow rate. So, if we have to control what happens, this is the way or piping system through which fluid flows, and we can monitor the flow rate by using this flow meter. If that already calculated mass flow rate could not be controlled, then it will be difficult. So, for controlling purpose, we can use this bypass valve, and we can fix it what mass flow rate is. You have already set to pass through in the flat plate collector. Okay. And this part is for heat exchangers, right. there are many difficult situations, there are number of test processes. So, what test process we are going to explain is under steady state condition. So, what will happen under steady state condition? So, the standard testing standard specifies that the collector shall be tested under clear sky conditions to determine its efficiency characteristics. Okay? So, if your climate is not favoring you, that means there is no clear sky, then what you will do? It is very difficult, because normally these experiments are performed on a clear day and during the midday, or when sun is on your zenith. Okay? It starts at 11:30, then you take 4 readings till 1:30. So, at least 4 set of readings you can take, and that has to be continued for 4 days. So, minimum 16 set of data is required to characterize a flat plate collector. Okay? And that too you are making at different mass flow rates and inlet fluid temperature, right. Now, condition is, suppose you do not have clear day and cloud is covered, okay. Only hardly you will get 2-3 hours time, then how you will perform the experiments? It is very difficult, right. So, that is how people are doing transient analysis, by noting this delta t. So, at certain period of time how delta t is changing, and from that they are configuring, that could be the profile, because we need to perform it. So, here the kind of test we are going to explain, it is under steady state condition, but in case of when there is very limited solar radiation, but still you want to perform the characteristics of a flat plate collector, you will go for transient analysis. Okay. So, this is very important. So, what are data you are going to record? It is mass flow rate and TFI. So, these two you are going to fix it, and then other things you are going to record, right. What will be the fluid outlet temperature, okay, and then other parameters. And you need to measure flow rate, then outlet inlet temperature, solar radiation, ambient temperature, and wind speed, right. So, that is how I said you need to start experiments at approximately 11 o'clock, and then you finish by 1 o'clock, okay. That is the solar noon. So, that time you consider and do the experiments, and during this test under steady state condition, so any bias due to transient conditions is eliminated. Okay. Also, you can see what are the conditions while testing the solar flat plate collector. So, solar radiation should be always more than 600 watt per meter square, even though we can write it is suggested 700, but if it is more than 600 is fine. Okay. And what could be the global radiation variation? Normally what happens, we prefer to conduct this, but this solar radiation is varies, okay, and 1 hour time we consider it a like under steady state condition, right. So, we consider if the variation is plus minus 50, then we can perform the experiments. Okay. Then ambient temperature, it should be plus minus 1 degree Celsius, then flow rate maybe plus minus 1%, fluid inlet temperature maybe 0.1 degree Celsius, and then temperature rise across the collector is plus minus 0.1 degree Celsius. That much of variation is all right for doing the experiments. And also we need to check the wind speed. What will be the wind speed? If wind speed is very high, then we are not suggesting, because what happen if wind speed is very high, then you are actually promoting more heat transfer. So, that is also not suggested, because these sets of experiments were performed by many researchers, and after doing so many calculations and research, they have concluded. So, this range is sufficient to characterize a flat plate collector, right. And of course, mass flow rate you can see 0.02 kg per second per square meter of gross collector area. Okay. That is the condition or constraint you can say for designing a liquid flat plate collector. Now, as I have explained in the first class, why to develop this Hotel-Wheeler Bliss equation, And earlier when we define QU, which is nothing but useful heat gain, right. So, useful heat gain, how we have calculated, you remember, right. So, once you know the amount of solar which is absorbed by the absorber plate and then losses taking place from the top, sides and the bottoms, then we can perform what is no QU, right. Very easily you can calculate, right. We have solved that long problem in trial and error method what we have solved. So, once we know that, then we can find out, but our approach is, can we express this useful heat gain in terms of fluid inlet temperature. So, while doing so, we have developed this expression called Hotel-Wheeler-Bliss equation. QU is Fr multiplied by AP, which is the plate area, and then S is the amount of flux received by the absorber plate, then UL TFI minus TA, right. So, if we divide this expression by AC by IT, this is the collector area, because in case of collector system we can define the efficiency in terms of maybe gross collector area or maybe plate area. So, both are possible. Okay. So, what we have expressed first, this expression in terms of collector gross area. So, QU is known to us, this is MCP TFO minus TFI, that means difference between the outlet fluid temperature and inlet fluid temperature, okay, and mass of the water which is circulated, and Cp is the specific heat of water, and AC is the collector gross area, and IT is the amount of radiation which is falling on the collector system, not in the absorber, right. Now, we know this expression, and this is very useful expression, and if we divide this expression by AC multiplied by IT, then you will have this expression, right. Now, this is nothing but your instantaneous efficiency, what we have defined before, right, and this is nothing but this expression by S into IT, and then this is divided by IT. So, you have IT at the bottom, because AC is out from the entire expression, and also we know this S, the amount of radiation flux received by the absorber, is nothing but the amount of radiation flux which is falling on the glass cover or maybe collector system multiplied by tau alpha average. So, it take care of both diffuse and normal radiation, right. So, we can write it like average tau alpha values, because in our previous lecture we say it is a classified way of doing the calculations. Okay. So, if we know this tau average, we can multiply some parameters, then we can find it out. Okay. So, this S can be expressed in terms of IT and tau alpha average, and if we substitute this expression, we will get an expression of this kind, okay, tau alpha, and then you will this expression. Now, if you look it very precisely, it will be something like a straight line equation, okay, because these all are constant for a particular collector. AP is constant, AC is area, and this is Fr is constant, already this is the resistance offered, but the heat flows from the collector system to the fluid. Okay. So, how much radiation actually is not allowing to go there, actually it is like a resistance, thermal resistance, and this is the overall loss. Okay. So, that means this part, if you multiply with this is like a y is equal to mx plus c or minus c. Okay. Here what you can see is a minus c. So, it is like a straight line equations having the slope of this part, and this is the this is intercept, sorry, this is slope. Okay. That means this is y, this is m, this is x, and this is c. If we define something like y is equal to mx plus c. Okay. So, this is like c minus m into x if it is y, if we define as y. Okay. So, we can actually make something like this. So, this equation comes from some kind of experimental commercially available collector systems, and they found that this is something like this. Okay. So, if we plot it, so you can next slide you can see how we can develop the plot, and we can find out these m and c values. So, this kind of expressions you will get finally. So, that means if we plot efficiency and you have this parameter, then you will get a straight line, and that is a negative straight line. Okay. So, you will get something like this. Of course, you will get a lot of scattered data and you need to fit the straight line, and you can develop an expression. So, finally, you will get this kind of expressions for a collector. AP by AC is 0.99. Already you know this plate AC is about 1.2 times AP. Okay. So, this kind of assumptions also you can make. Normally, it is 1.2 times more than the observer area, and this parameter is about 0.909, and then we can find out FR tau alpha average is how much and FR UL is how much. So, in certain cases, if we consider AP and AC are same, maybe we can express this instantaneous efficiency in terms of plate area. Then what happens in the earlier expression, what we said, this will be 1. So, you do not have to think much, and then its complexity somewhat reduces and you can find out. So, once you know this, then you can develop this kind of expressions, and then it is very easy to find the efficiency at certain conditions when you know the fluid inlet temperature, ambient temperature, and then radiation. Okay. Because at the particular time you must know what is the intensity of radiation, then fluid inlet temperature and ambient temperature. Okay. So, then you can plot this KFI, and what equation what you get, this is a commercially available solar collector. And this collector is having a gross area is 2.27 square meter and mass flow rate of 0.0456 kg per second. Okay. So, you can get this kind of expression, right. Now, so as I said before, for liquid flat plate collector, so why single mass flow rate is sufficient to characterize a flat plate collector? Because change in mass flow rate do not appreciably affect the performance, because the relatively high values of liquid size heat transfer coefficient. This is very fundamental. So, once you could answer, then it is fine. So, this is because of the liquid side heat transfer coefficient. And for this reason, although the efficiency curve of a collector is determined for a particular values of mass flow rate, it can also be used for predicting the behavior of the collector for other mass flow rates which differ a little from the values used during the test. Okay. So, it is clear to you, right, why actually we single mass flow rate is sufficient for characterizing a flat plate collector. And if we talk about the performance over a day, so what actually we are getting, it is something like this, and we really want this kind of pattern, right. So, it will be something like this kind of pattern. So, if we plot it, then you will have this kind of informations on a clear sky, and this kind of information or this kind of data is important when characterizing a flat plate collector, and of course, this kind of weather is required for doing the characterization. Okay. Now, if I take an example of this kind, say a liquid flat plate collector has the following characteristics parameter. So, FR tau alpha average is given and FR UL is given to you, and it is operating under the following conditions. Solar flux incident on the collector is known, and then water flow rate is known, and it is 0.015 kg second meter square of the observer area. Ambient temperature is known, inlet temperature is also known to us. We need to calculate the mean absorber plate temperature of the collector if the collector efficiency factor is 0.9. Okay. And interestingly, if the circulating pump fails, what is the maximum temperature attained by the plate? So, in the last session, Professor Christophe has already explained what happens. suppose if you are going for during the weekends, then what kind of measures to be taken, right, for say household flat plate collector. First thing, you can cover the flat plate collector. Second thing, you can release the water and open the valve to release the hot water. Okay. So, now my question is, what maximum temperature you could achieve under that condition. So, if you left for during the weekend and you have forgotten to turn off the system, then what could be the maximum temperature on that day. So, it is related to the last discussion held. So, can you process? I have given those equations required to solve this problem. So, what is QU for Hotel-Wheeler-Bliss equations, and then in terms of mean plate temperature and then FR values. Can you tell me some of the things like I will just help you. So, we know the instantaneous efficiency, which is FR tau alpha average minus FR UL, then you have TFI minus TA, then you have IT. Okay. So, what is this value? FR tau alpha average is 0.68 minus FR UL is 6.1, and what is this value here? TFI minus TA is 40 minus 20 is 20, and what is the solar radiation? It is 900 watt per meter square, right. So, you will get a value, you can cross verify it, it is about 0.544, that means 54.4 percentage. Okay. And also instantaneous efficiency, which is defined as MCP, then you have TFO minus TFI, and you have in terms of plate gross area, and you will have IT. Okay. So, here mass flow rate kg per second per meter square of the observer area is given. So, that means this area is this information is given to you. Okay. So, this information is something like 0.01 kg meter square second square meter square, okay, second meter square, and you substitute this IT and CP values, then you can find out what is the instantaneous efficiency here. So, instantaneous efficiency is also known to us 0.544. Then what else you can TFO, right. So, TFO you can find out. So, as per my calculations, it is 47.8 degrees Celsius. Okay. So, you know these expressions for FR expressions are known to you, and collector efficiency factor is 0.9, is FR is given to you, right. FR is given to you, and also you can do something on so here FR UL is 6.1. So, you can find out UL here is UL will be your 6.1 6.1 by f of r. Okay. This is also one expression, so you can use it, and f r tau alpha, and from the other expression from here there is tau alpha average will be 0.68 divided by f of r. Okay. So, how will you find out f r values? F this is given actually, no. If the collector efficiency factor, this value is nothing but 0.9. Okay. So, we need f r. Can you do some kind of adjustment? So, anyway these values are known to us. Okay. And that means, and this is also known to us. Okay. So, if we could express UL in terms of f r, then I think we can do it. So, can we express UL in terms of f r? So, UL is 6.1 by f r. So, if you substitute that, UL is equal to 6.1 by f of r, then actually we can find out. So, that means f r is equal to, then you have UL is 6.1 by f r. So, this f r will be here, and then you have 6.1, and this value is known. This value is 0.015. Okay. Sorry.
Below UL.
Yeah.
That can be put in the next slide.
Yeah.
For UL value are already given. 6.
Yeah. This f r will goes off. Only one f r will be here. Yeah. So, from here you can find out what is f r. So, I am not going to write the things. So, from here what you will get, f r is equal to 0.83. So, which is in the range what we have explained before. So, once we know f r, then we can find out what is UL. It is 6.1 by 0.83. So, this is 6.1 by 0.83. Then you can find out what is UL, right. So, everything is known here now. F r is known, then we have UL is known. Okay. Then S is IT by tau alpha average, which is also known, because tau alpha average is 6.8 divided by f of r. F of r is known. Okay. So, everything is known. So, we can find out what is QU, and then once we know this QU from here, then we can substitute here and we can find out what is TPM. So, plate temperature we can find out once you know QU, and that is known from this expression. Okay. So, this Q or maybe what I can say here, QU by AP, you will get a value of about 498.01 watt per meter square. And if you substitute here and do the arrangement, then from here you can get TPM is equal to 50. It is 53.8 degrees Celsius. So, this observer plate temperature of the collector, we have done it. Okay. So, this problem is very important as far as exam is concerned. Okay. So, TPM we can find out it is 53.8 degree Celsius, right. And what could be the second part of this problem? If the circulation pump fails, or maybe you have forgotten to turn off the system, then what could be the maximum temperature of the collector or maybe fluid? So, as you know, if the temperature increases, then that may damage many of the components of the collector system, right. So, what will happen? That means you are not collecting QEV 0. If QEV 0, you are not collecting the useful heat gain, then what will happen? This part is 0, then this is equal to this, that means S is equal to AP, that means what? S is equal to UL TPM minus TA. This TPM will be how much? You can very easily calculate, right. So, circulation pump fail means you are not using the useful heat what you have generated. That means QEV is equal to 0, and then you can maximize the temperature, or you know what is the design temperature or stagnation temperature. Okay. So, as per my calculations, it is about 120 degrees Celsius, close to or approximately, for this approximately 120 degrees Celsius. You can see here TPM we got 47.8, but when you are not collecting, temperature rose up to 120 degrees Celsius. Okay. So, it is really significant, right. So, this kind of things are very essential to consider as far as flat plate collector is concerned. Okay. Fine. So, I will move to the next slide. You got it, right? Problem is understood. So, few data are given, you have rearranged the data to find out this QU. So, once you know QU, then you can find out what is the plate temperature, and then if circulation pump fails, that means you have forgotten to turn off the system, then your temperature might rise to a very high values. Okay. So, that is nothing but your stagnation temperature. So, these are the calculations. So, now this testing of solar air heaters we will study, and then some of the applications of solar air heaters in drying and electricity generations. So, here this solar air heater test procedure is almost same, but here since we have sensed the working fluid from liquid to air, then we need to perform the test at different mass flow rates. Okay. So, we need components like the solar air heater, a blower. So, we need to blow the air here, and earlier case we use pumps. Okay. So, that was liquid, and an apparatus for conditioning the air, which ensures that the air enters the air heater at the desired temperature. So, inlet temperature has to be fixed. Okay. So, that is how this reconditioning apparatus will be there, something like heating, sometime heating with heat exchangers. If it is not sufficient by the solar radiations, then we need to recondition it. Okay. Then we need to supply, and there is a mass flow meter, orifice meter. Okay. That is used for, or maybe sometimes other arrangements can also be suggested for measurement of air, and that regulated flow will flow through this blower, because blower will act on it, and then it goes through this solar air heaters. It may be single pass solar air heater, or maybe double pass solar air heater. That depends the kind of solar air heater you are using, or it may be air heater with fins, or maybe some other arrangement, or maybe it is a PVT system. Okay. If there is a PV cells, and then you have absorber, and then you can blow air under the absorber. Okay. So, you can fix it here. Interestingly, you can see there are many thermocouples attached here before entering to the air entering to the system, and also there are mixing vents because it's air. So, there will be non-homogeneous temperature, right? At different positions temperature will be different. So, in order to uniform or uniformly measure the temperature, so this kind of vents are attached, and then finally what we are measuring is the fluid outlet temperature, and that too not only single thermocouples, we are averaging the temperature, okay? Because temperature will be different. It is not liquid, it is not molecules are dispersed, it is not very closely packed. So, the temperature measure at different locations will be different, it is not constant, right? But we need to take the average of the temperature. And this delta P for solar air heater, pressure drop is very essential, okay? And we have discussed in the very beginning class that what are different arrangements we can make. We can use some kind of what is called matrix to increase the heat transfer coefficient, okay? But at the same time we are actually increasing pressure drop, right? So, pressure drop in this case is very essential, okay? Even though there are certain arrangement which actually augment the heat transfer process, but it might reduce the pressure drop or maybe increase the pressure drop or maybe increase the power required to blow the air is very significant or very high, right? So, we need to decide what arrangement will be best, and that is how we need to know what is the delta P here, and this is the manometer. So, we can find out what is delta P, and from that we can find out really what is the pumping power, which is already explained by Professor Christophe in his one of the classes, like in friction factor, and then if you increase the roughness, then what will happen, what is the value of friction factor for this kind of conditions, and then accordingly what could be the delta P values, and that means pumping power, okay. So, this measurement techniques you must know very precisely, and also why this kind of arrangements are made and what benefit you are going to get, this is very important, okay. And then we can do the experiments at the different mass flow rates, and we can find out this characteristics curve, and then we do the analysis and characterization. So, you will get this kind of scatter data, and again we need to have different fitting coefficients and generate some kind of plots and then equations to relate this instantaneous efficiency and this parameter here. So, earlier things were different here, and here what happens, we are using this mean temperature, okay. TF bar, it is a mean temperature of the fluid, and then minus TA, then IT. So, this parameter we need to investigate to find this efficiency, okay. We have a very interesting problem which I will solve now. So, this is quite interesting problem. So, efficiency curves shown in this figure are obtained for a solar air heater of dimension L1 is 1.2 meter and L2 is 0.9 meter, that is a dimension, which is tested under a range of flow rates varying from 25 to 200 kg per hour, okay. So, different flow rates, okay, because of heat transfer coefficient, and we need to find the efficiency which would obtain and the corresponding mass flow rate if the air heater is used under the following conditions. So, air inlet temperature is 54 and outlet temperature is 74, ambient is 26, and solar flux incident on the glass cover or through the glass cover is 950 watt per meter square. So, how to proceed with this? So, characteristics curve is something like this. It is TF bar minus TA divided by IT, and this is the unit of this parameter, and this is the instantaneous efficiency, and this what you can see at different mass flow rates, characteristics are something like this, okay. So, we need to find out now efficiency and the corresponding mass flow rate, that means the optimized mass flow rate, and we need to rely on trial and error method. So, can we initiate like now values are given to us and as I said, T f bar is nothing but you have average fluid temperature, and this is like, if you know, this is average fluid temperature. I will write average fluid temperature, and this is something like T f o plus T f I by 2. Okay. So, fluid inlet temperature, outlet temperature is known to us. Then what could be this T f bar? It is 64. So, once we know T f bar, then we can find out this parameter T f bar minus T a divided by I t, right. So, I t is also known to us, it is 950, this is the I t values, and this is 64. What is the ambient temperature? Is 26, right, and I t is 950 watt per meter square. So, if you substitute, then what value you will get? 0.0. But here what I is a kilowatt. So, kilowatt means it is fine. So, then what you will get? It is 40. So, your unit will be meter square kilowatt, right. So, unit is kilowatt, that is why I use kilo, and that means this is something like your 0.95 kilowatt per meter square. Okay. So, then if you know this parameter 40, so this is 40, okay, and you go up here 40, and this is the point, and this is actually 25 kg per hour mass product, and you find out what is the corresponding efficiency. Okay. So, this is the corresponding efficiency. So, if center is 25 here, it is less than 25. So, to be precise, as per my calculation, if we assume, okay, if we assume m dot is 25 kg per hour, then efficiency will be at this value, it is 24.2 percentage. So, 24.2 percentage. Okay. So, if this is the value, then can we find out what is Q u, because we know this is equal to Q u by I t into A. Okay. So, this is, or it may be, this area is given to us. So, if you go back from here, what is the area? 1.2 multiplied by 0.9 is the area, and efficiency is known, then you can find out what is Q u in this case. Q u we can find out, this is 0.242, then you have 950 and area 1.2 into 0.9. Okay. You can find out what is this value. 248. 248. What is the unit? What? It is what? It is what? It's fine. So, 248 you got, and then we know Q u is equal to m C p delta t, and it is 248. And C p of air, maybe you can consider like 1007, that is 1.007. Okay. So, Cp of air 1.007 into 10 cube or maybe kilojoule or joule per kg Kelvin or degree Celsius. So, you can find out what is m. So, I want in kg per hour 248, Cp is 1.007 into 10 cube. Okay. And then you will have delta T. What is delta T here? What is the value of delta T? 74 minus 54, it is 20, and then here it is 3600, because I want in kg per hour. So, what is the m that value? 44 point. Kg per hour. See, we have started with 25 kg per hour, but what we got is 44.32 kg per hour. So, our assumption is not valid. Okay. Now, again we need to go back and see what next we can do. Okay. So, it is 44.32. So, what we can do? We can get it say about 50 kg per hour. So, if I take 50 kg per hour, so the same line you go up and this is for 50, and if we extend it something like this. Okay. So, this value we need to find out. So, precisely as per my calculation, it is about 28% efficiency at this condition. So, if we consider m dot is 50 kg per hour, then instantaneous efficiency is 50, sorry, it's not 50, is 28%. Okay. So, if this is the case, so can you tell me what is Q here? So, this is 0.28, then you have 950, then this area 1.2 multiplied by 0.9. Okay. So, what could be the value of Q? 287 watt, right? And then what could be the mass flow rate? Use the same process, then the mass flow rate will be how much? 287 multiplied by 3600 divided by 1.007, this is specific heat of air, then you will have 20. 51.35. So, we are somewhat close, right. So, now we can take this value and do the calculations, then you will find it is very close to these values. Okay. That means, we need to do trial and error till we get a very close values of 2 iterations. Okay. Then you can close the calculations and you can say that that is the final values. So, that is how we can do. See, we have seen at different mass flow rates, and initially we assume that it is 25 kg per hour, but this is not actually 25 kg per hour. So, then we have revised our assumptions, and we got a value which is close to 50, it is 51.35. Again we need to do one more time at this condition in order to strengthen our understanding that that is the correct values. Okay. So, once it is finalized, so if by taking these values you will get a value of somewhat like 51.5 again. If you take these values, then you will get 51.5. So, that means this is very close values. So, this is fine for us. Okay. So, you got it now why you need to do experiments at different mass flow rates. Okay. So, that is the basis of doing this calculation, right. Let us move to the next. So, now we will spend some time on solar drying of agricultural products. So, why do you need drying? So, in most of the times people approach us for solutions for effective drying. What drying process we can suggest, and what could be the best drying methodology and device for meeting their demands. So, drying is required for many conditions, like say for example, if we talk about paddy, we need to dry, it is open sun dry only. So, there are a lot of losses taking place when you do open sun drying. A lot of insects will take, and then a lot of when you collect this, lot of losses will be there. Of course, these losses are important for other animals or maybe birds. Okay. So, everything is required, but no, if these losses are very significant, then you need to take a measure. Okay. And also sometimes what happens, you have harvested the paddy and you need drying, but season is not favoring you for drying because of rain and other climatic conditions. Then what could be the solution? Because you harvested for a long 4 months time, and then you could not dry it. Because of that, you cannot spoil the entire paddy what you have harvested. So, we need a clear cut methodology to dry it. Not only paddy, say for example ginger or any other spices, maybe cardamom. You have got plenty of cardamom, plenty of gingers. Then how to preserve those? Because in as per report, many of the agricultural things as wastage because of improper drying and non availability of dryers. So, that is the basis of requirement of drying. And what happens, why this has not gained so much of popularity? Because drying has to happens for a particular period of time, not throughout. Like a paddy, it harvested for a particular period of time, and rest of the time your dryer will be ideal. And then ginger will be harvested for a particular period of time, and for that period of time you need a sophisticated dryer, and rest of the year it will be ideal. Okay. So, can we have a drying methodology which will serve for all the spices, all the vegetables, or maybe all the other grains? Okay. That's the thing we should emphasize in order to have sustainability. Okay. And design of solar dryers are based on empirical and semi empirical data than its theoretical design in most of the cases what we see. And majority of the solar dryer designs are used mainly for drying various crops, either for family use or for small scale industrial production. Okay. Large scale things are not there as far as solar dryer is concerned. So, really it is a need of the hour, because agricultural things are increasing day by day, because population is increasing. We need more food, more spices. So, we need sophisticated and reliable drying systems. So, how this drying happens? So, drying means in the raw biomass it contains a lot of moisture, right. So, that the moisture has to be removed. Moisture means water. So, that is how large portion of energy consumed during drying is for transforming liquid water into vapor. So, it is latent heat need to be removed at atmospheric pressure, and water may be contained in various forms. It may be free water at the surface, or may be bound water which is inside the grains. So, it is very easy to remove the water which is above the surface, which is touching the surface, and there are some water which is inside the surface, it is very difficult. Okay. The free water is regarded as unbound, and the product is not hygroscopic, and bound moisture is trapped in closed capillaries, and the material is called hygroscopic. Okay. So, it is something like you need to provide energy and then evaporate, and particle will be dried, and your moisture will be out. And this hot air involves the simultaneous action of heat and mass transfer. So, here both heat and mass transfer will happen. So, heat is provided and mass transfer will take place. Okay. And also this moisture content can be expressed in either dry or wet basis. Okay. So, wet basis we represent something like mass of water to the sum of mass of water and mass of dry solids. Okay. And dry basis we consider mass of water to the mass of dry material. Okay. So, how this drying happens? Okay. So, here what you can see, we are representing this drying, that is dt by dx by dt, and which is running by mass per rate of drying, it may be kg per hour. So, and in the horizontal axis what you see, it is drying time. So, AB, what is AB here? AB is the time spent to heat up the material until the drying temperature is achieved. Okay. Then we will go for BC. BC is the constant rate drying. Then what happens? It will be constant, drying is constant. Okay. And then this C and E is a falling rate drying, where a flow of moisture from mass interior is decreased continuously. Okay. And these things happens in majority of the grains and vegetables. And E, there is still moisture inside the product, and moisture removal takes place slowly by diffusion drying, that stops at D. Okay. So, that is how it stops, it goes moisture removes, then constant, then falling, then again it continues slowly because of diffusion, and it reaches at point D. And this is the drying characteristics for most of the grains. Okay. So, this is very interesting, and then when you are studying drying kinetics, the knowledge of this plot is very important, how really it happens, and then you can do some mathematics and you can find out the parameters. And water activity is also important for fruit preservations, as it is a measure and a criterion for microbes growth and probably toxin release of enzymatic and non-enzymatic browning development. So, this is very important, as you can see here, mathematically we can express in terms of partial pressure of water solution to the partial pressure of pure water at the same temperature, and majority of the bacteria grows if this value of water activity is equal to 0.85, and mold and yeast grows at about the water activity of 0.61, and fungi grows at about less than 0.7. So, these values are very important as far as microbes growth in the substrate is concerned. So, for every food or any kind of agricultural products, there exists an activity limit below which microorganisms stop growing. Okay. So, that we need to find out. And also we must know what is equilibrium moisture content, which is defined as the moisture content when the vapor pressure exerted by the moisture products equals the vapor pressure of the nearby ambient air. So, it is related to vapor pressure. Okay. And also this is sorption isotherm, knowledge is important, but there will be hysteresis. It is not always the same thing while absorption and desorption, there will be hysteresis, and this is also important. When you plot it water activity versus water content, then you can get this kind of plot. Okay. So, we will be solving a problem say for example, we consider grapes drying, and then we will calculate all the parameters, how much amount of energy and other things are required for drying certain quantity of material. And this as far as drying classifications are concerned, it may be active dryer or maybe passive dryer, that means natural circulations and forced circulation. You need to provide fan or maybe blower over the substrate in order to accelerate the process of drying. Then we will have direct and an indirect mode and maybe mixed mode. Okay. And direct is a box top dryer, indirect is a cabinet dryer, and the mixed mode is like a tunnel dryer. So, people are doing a lot of mixed and then a hybrid drying system nowadays. So, we got a project recently, and that is on how to utilize biogas for drying purposes. So, biogas we are using and then purifying it, and then we have heat exchanger, and maybe at the top we have cooking, and then we will exchange the heat, and then we have a PCM storage, another heat exchanger where PCM will be stored, so that we can extend the drying process. And why this kind of dryers are required? Because if you do not have solar also, solar radiation on certain period of time, you can run the systems, or maybe at night times if you want, you can actually do the drying process. So, it is a greenhouse dryer plus heat exchangers. There are many heat exchangers, and then you will have what is called other reactor like anaerobic digester, from where you can produce some kind of fuel which is burned for increasing the heat. And this kind of cabinet dryer, you can see solar radiation is passing through these glass covers, and then this moisture from the vegetable and then grains will move up, and then drying happens and air is supplied from the bottom. And you can see this is forced circulation dryer. So, it is like direct grain. So, it is attached to the grain. So, air will be pumped through a blower, and it goes through this cover system, and then it is passed through this trays, and then finally this will blow out. Okay. Or maybe blower, sometimes you can attach it will suck the air. Okay. And that is how it is drying is done. And this is indirect grain forced circulation mode. We have blower and solar air heater is there over the solar air heater. That means maybe inside the solar air heater, hot air carries, and then it pass through this material. Feed will be here, and dry product will be collected here, and air will go out. And this is forced circulation. Already these kind of systems exist. And now one more very interesting thing you can see here as far as dryer is concerned. So, solar chimney power plant. So, what you can see here, this is a turbine, it is air turbine, okay, and these are transparent covers. It is like greenhouse. So, temperature maybe up to 20 degree you can rise, and then because of this density difference, it goes up and turbine rotates, and you can produce electricity out of it. And it is very, very tall. You can see here, this is like greenhouse, okay, and there is a gap, and it is a plenum. Air moves through this and then goes up, and air turbine should be placed in some of the locations here in the tower. Okay. So, here it happens. So, it consists of this central chimney, then greenhouse. So, these are a circular greenhouse, what you can see here, and of course, it is a transparent, and we need a very strong metal stand, so that it can hold the structure, and we need a fan and generator. So, it is a air turbine. So, it is a turbine will be there, and Dr. Mebratu, he has developed one compressed air energy storage systems. He also used the air turbine there. So, compressed air goes, and then it rotates this air turbine, and then generator is coupled. The similar kind of things. So, air moves up and rotates, and then there is generator. You can generate electricity. So, in Spain you can see this kind of installations in desert place when you really require some kind of electricity, right. So, you do not have many options, but this kind of systems can be installed to get some kind of electricity out of these solar radiations. Okay. And just we need to define what technology will be suitable at that location. So, chimney is about 200 meter tall chimney and diameter is 10.3 meter. 10 meter is really big, right. So, it is 6 meter and then multiply with 2 and that many big, that is a diameter. Okay. And you can see this is the radius. Okay. It is a big one and that is how many turbines can be installed in that pole. And solar collector area extended to a radius of 122 meter from the chimney with glazing being 1.8 meter above the ground. So, this glazing are there. Okay. It is not open, this is glazing is placed, so that we can get more solar radiation, and area of the glazing about 46,000 square meter. It is really, you need a barren land. We cannot use our vegetable or visiting place or what is called important place. Then there are 4 turbines of 5 meter long blades and rotates at 1500 rpm. So, 4 turbines are placed, not only single turbines, 4 turbines are placed in that place, and it produces 50 kilowatt of power. Okay. And this, of course, this energy conversion efficiency is very low because temperature is very low, right. So, maximum conversion efficiency as calculated, it is found to be a function of height. As you increase the height, then you are expected to get higher conversion efficiency, and these all parameters are close to constant. Okay. So, TA and CP, how much TA will change? Not change much, because of course, it will be climate dependent, but it is a function of H. Okay. So, height of the chimney tower and temperature of the ambient air. Okay. So, can we just quickly solve this to get an idea about its efficiency. So, we assume that height of the chimney is 300 meter, solar collection area of the greenhouse is 50,000 square meter, specific heat of air is given to you, ambient temperature is known, and assuming the turbine generator set converts only 50% out of the maximum available energy into electrical energy, and the collection efficiency of the greenhouse is 25%. So, by considering this, can we calculate the maximum possible conversion efficiency by this chimney, and also the daily electrical output in a typical summer month having solar radiation 6.5 kilowatt hour per meter square. So, we need to also estimate the efficiency and then daily electrical output. Can you just tell me what is the maximum efficiency by using the expression? Eta max is GH by CPTA. So, height is 300 meter, Z is 9.8, and then CP is 1005 and T ambient is in Kelvin in 305, right. So, it is, what is the percentage? 0.96 percentage. I think you have never seen this kind of percentage in life. It is 0.96 percentage, it is less than 1%. Okay. It is very inefficient, but we can generate some amount of energy. Okay. What could be the overall efficiency? it's 25% is the collection efficiency, then we will have what is called maximum efficiency is known, and then we will have turbine generator set converts only 50% of the energy. So, overall is 0.0096 into 0.25 into 0.5. Okay. Then multiplied by 100, it will be how much? .12. Okay. So, how much is the daily electrical output of the plant? So, it is 6.5 kilowatt hour per meter square, and then you have collection area is 50,000. 50,000 is the collection area. So, overall efficiency is known. So, what really we want? Daily electrical output of the plant. Daily electrical output of the plant. So, this is overall efficiency is equal to electrical, and then we have 6.5 kilowatt hour per meter square multiplied by, you will have 50,000. So, we can find out what is P. How much is the result? So, this is overall efficiency, okay. And then you want this electrical output. Output by input is efficiency, right? So, output is P, what we want, and input is solar radiation and area. So, in my calculation it is about 390 kilowatt hour, 390 kilowatt hour. Okay. So, in there is a plant in Australia, its capacity about 200 kilowatt, 200 kilowatt, yes, 200 kilowatt, it's electrical, 200 kilowatt electrical, and it is 1 kilometer tall. It's 1 kilometer tall, and then about 7 kilometer diameter is the base. So, 7 kilometer is the diameter base, and then 1 kilometer tall. Okay, it's interesting. Okay. Okay, then. So, these were some of the informations about solar air heater. Okay. Now, let us move to the standards for solar thermal collectors in the world. It is very briefly, I will just explain the standards because as I said before, standards are very, very important. Otherwise, there will be no restrictions, like everyone will produce, and then you do not know about its longevity and other performance parameters. Then people will be complaining like, no, this will not work, but this is not the case actually. If you set some kind of targets as far as quality is concerned, then everyone will be happy. Okay. But as professor said in one of the classes, like, strength has to be something like this. He has used in the freeze, right, that he said about his experience to see the strength. It's really worked, it's very good strength. So, that is also one important parameter. So, quality control parameters, like, we need to check the material quantity, like its glass cover, what could be the quality of the glass cover, okay, and what could be the material of construction for the glass cover, then absorber plate, okay, and then what are absorber coatings. So, all the things need to be specified, okay, insulations, then thermal performance, it may be efficiency testing and stagnation temperature, which is very very important. I was repeating this. So, these are very interesting thing, and then structural integrity. So, leakage test is very very important. So, if you are making something and the leakage is happening, then what will happen? So, we need standards in all the aspects of the components and design, right. Say for example, if we talk about glass cover, as I said very briefly, what could be the extinction coefficient for your purpose? What is the strength of the glass cover? So, these are very very important things. Then for coatings like selective coatings, what could be the absorptivity, what is the emissivity. So, all the things should be very precisely written in the system, so that no people will be convinced like okay, longevity will be something like this. If it goes beyond the limit, then it will not work, and this is the appropriate range of working conditions. So, all the information should be highly it should be written and then highlighted in the specification sheets. And efficiency is important, how much energy you will get at the end, and then thermal stress is important, because if hailstorm happens and broke every component, you are gone. And if it is a big plant, then all that money you have invested, it will be just no use. So, at least some the strength has to be there to resist those shocks. And this ISO standards for flat plate collectors. So, IS 12933-2003 is the standard for flat plate collectors. Still they are amending those what is called standards, because time to time we need to revise this, and that is how there is a big meeting, and Bureau of Indian Standards, they are actually looking into it to strengthen those norms, because you do not know from where these collectors are coming. It might be very low in quality and then other parameters. So, this is important. So, all evaporated tube solar water heating systems standards are there in 2016. Then all glass evacuated tubes water heating systems, we have standards of 16542, it is also formulated in 2016, and the source is MNRE website. And this is the standard, and you can see this all the components are very precisely mentioned for this IS 12933, what could be the quantity and what could be the strength, all the things are listed in the standards. Okay. And quality control test is routine test we have, like static pressure leakage test is one of those, and external thermal shock test is also important, then thermal efficiency test. So, these are primary things we need to concern about as far as quality control is concerned. So, there should not be pressure drop, that means from that we can find out whether leakage is taking place or not. Okay. Then no appearance of swelling, then distortion or rupture in the riser and headers. Then as far as thermal shock is concerned, there should not be any crack or distortion, then condensation of water penetration inside the solar collectors. So, once it is observed, then you can find out something is wrong. So, we need to be concerned about it. Then for thermal efficiency test, this characterization confirms something like UR UL has to be less than or equal to 5 watt meter square degree Celsius. This is one parameter. Second is like FR tau alpha average is greater than, it should be greater than or equal to 0.65. This is one of the important parameters as far as thermal efficiency test is concerned. And for BIS certification marking, these things has to be written on the device, who is manufacturing, its addresses, its serial number, then maximum working pressure in kilopascal or maybe some other units, values of these two parameters, FR eval and then FR tau alpha average, then observer material, surface coatings, what kind of surface coatings and what is the wavelength of absorption and emission, and then month and year of manufacturing and country of manufacture. This information has to be reported as far as the IS 12933 in 2003 is concerned. Then all glass cover evacuated tube solar water heating systems, you can see this IS 16544 2.16 is the standard time, and it's they say that the exposure to solar radiations on plate of solar collectors has to be more than 4.5 kilowatt hour per meter square for 2 days. So that's the things. That means 2 days they have to perform the experiments, and after preconditioning of 2 days all parts shall be inspected by any visual science, because it is like indoor experiments. So you cannot have constant 4.5 in outside, right? At night anyway it will be not there, and daytimes also it is varying. So there are some designs, confirmations and direct insertion of storage tank cell conforms to IS 16542. So these are all like part of the quality control of IS 16544. So this is just the information. And also for storage water tank for all glass evacuated tube solar water heating systems, there are some general requirements like outer cladding and outer ceiling shall be smooth without any crack or obvious scratch, and no coating peeling off. So these are some of the general requirements like sinking, and then maybe to avoid entry of any foreign materials, and test requirements like capacity of storage tank shall be within plus minus 5% of 500 liters as per IS 16542 2016 is concerned. Okay. And for this we need to have the knowledge of measurement of storage water tank capacity, then leakage test, and then performance test. So primarily these tests are to be performed as per the standards, and then we can pass them if they qualify the minimum requirement. And there are different standards in different countries. You can see S396 they have procedure for testing of unglazed flat plate collectors, and then what is the minimum requirements for solar collectors, SRC standard 100, then 300. There are different standards. In China also they have different standards, and you can see in Brazil they have one standard, and European EN 12960 factory made solar thermal systems and components. Then South Africa they have the standards, then Canada they have set of standards. So they follow different standards, but no basic requirement is same, that the kind of test we have shown through 3 different conditions, leakage and pressure drop, and then efficiency or thermal test. And for New Zealand and Australia, the design construction of solar water heaters and heat pumps is one. Then Japan, solar thermal collectors, then test procedure, GIAN 1425, then Korea, then Chile, then Middle East. So all the countries they have, and then this is very important as far as quality and standards is concerned. So with this I would like to conclude my speech, and in the second half we will continue that tutorial. We have 2-3 problems to be solved, and that will be like end of the session. So thank you very much. If you have any questions, then again we can discuss. So thank you. Thank you. So now we will break for maybe 10-15 minutes, 10 minutes, and then please come back here, and maybe we can take a photo this time. It's a group photo, but all people are not here. But should we wait till the next session? Last certificate पहले, but few people are leaving. I think. Okay. Okay. But one photograph we can take later on. We can also, maybe one photograph we can take now, and later on also we will take one more. Then we will say no, select the best one. Sure.
Ah, good. So it is 3,000?
Yes.
Ah, I've got in my after. Thank you. I start. Okay, so for this last lecture tutorial regarding my presentation, we will today focus on the global evaluation of performance of a PV central that we call performance ratio. As I previously introduced that to you, I said that it is a key parameter to see if the PV central is in a comfortable operating condition, is operate well, or if there is a problem. Okay, so it's important to have an idea of this performance ratio. There is here today we will mainly focus on the impact of some parameters on this performance ratio, internal parameters, so parameters that are linked to the PV central. Okay, at which stage we could lose some power internally to the PV central. But there is also external factors that can impact this performance ratio. That is could be the soiling, for example. Okay, soiling effect. Okay, before I will just introduce a startup that I'm co-inventor and that has been created in 2019. And the purpose of this startup is to be able to identify if there is a problem on a PV central, just analyzing the signal. So just analyzing the power which is generated, the power before and after the inverter, okay, and to be able to identify if there is a problem. But if there is a problem, it's not the more difficult thing. The more difficult thing is to identify the origin of the problem. Okay, and then we will do the tutorial. So the startup, which is going a spin-off from my laboratory, so is Heliocity. the main objective of Heliocity is to focus on integrated PV central, so at the scale of city. And city is a kind of extreme condition for operating because the temperature is usually higher in the city than in the rural area. Okay, we have seen yesterday why. There is pollution. Okay, so pollution means a kind of filter around the atmosphere. Nebulosity of the atmosphere is not so clear. And soiling means pollution means also potential soiling of the PV panels. Okay, different aspect. You have also shadow. It's stupid, but if you are installing your PV central and then few years later there is a building, it could have partial shadow and it will not operate very accurately. The other main problem is that the maintenance, you don't go every day on the tower, of the roof of a tower to see if everything is okay. It's more difficult to, in the urban, where most of the PV centrales are on the roof, less accessible than in rural when you have a full field of PV panels. Okay. So it has been created in 2009. Now the startup is in Grenoble, so it's at 50 kilometers from my place, from the Ines. So you see, it's also a mountainous area. And so the objective is that a lot of things can impact. So here you can see some snow, some partial snow. That means that there is partial shadow that will impact the wool production. You have the bird, of course, that create some dust. Okay, even if it is local, okay, you have a problem because you have a shadow point on your cell. Okay, so usually we find that in cities the performance that are real compared to what is expected is under of what is expected, or around 15%. So it's important. Okay. So it's important to identify the reason why. Okay. So the principle is to develop the product that is sold is a software as a service. Okay. SaaS. The software as a service is consisting to provide information about your PV central. Behind it is a combination between the modeling of the PV central. The modeling, we know a lot of different BIPV integration, facade, roof, on insulation, on an air gap, and so on and so on. So this is a pattern that is behind between the modeling and the analysis of what is provided by the PV central. So there is a period of learning, okay, to see if the model is consistent with the PV central. And after maybe 2 weeks of learning, then it will compute that permanently, okay? And as soon as there is a discrepancy, that means that there is something wrong, okay? Something wrong that could be linked to the PV central, a cable which is cut, dust on the PV central, or from the surrounding. That means that maybe there is a building construction in the surrounding. Maybe there is a crane which some few hours during the day generate shadow on the PV central. Okay. So first it consists to have a kind of audit of the PV central. As I told you, the performance ratio, for example, what is a good performance ratio? That means that you have no worries to have. You remember the value? It was 80%, 0.8. Okay. If the performance ratio is at 80% or more, that's good. No problem. If it is under 80%, that's not so good. There is a problem. The problem could be since the beginning, because the PV has not been well integrated. What is well integrated is that you put your PV directly on the isolation. For sure, for this configuration, this PV panel will overheat. Okay, it's not absolutely not ventilated at the back side, so for sure the temperature level will be higher than expected, and the power generation lower than expected. Okay, so it is some problem like this because you have to leave at least a air gap between the PV and the building. Another problem that could be a small self shadow. That means that you have on your roof a chimney, okay, or a ventilation system, and the installer put PV panels around this. That means that during the day it will generate shadow all the day long. A small shadow, but a shadow. It's happened also to have such a problem. That means that since the beginning the PV central has not been well integrated. Okay, so the audit is necessary, but after it could be also problems that appear later, and then the software as a service allow to have a continuous performance monitoring. The main issue or the main challenge was not to go, if you have a customer that have a big PV central integrated on the roof, is not to say, okay, we will monitor your PV central, we will put a meteorological station, we will stick several thermocouples. Okay, no, it's too heavy. It's just analyzing the production of the PV central without any other sensors. Okay, so it is a challenge. Okay, so it is based, so as there is no local measurement of meteo, we are basing our analysis on the PV production. It's easy, what is the power which is generated, but coupled with satellite data, okay, to have an satellite and meteorological data in order to have, of course, an estimation of the local environment. And the modeling has also considered how to transform satellite data in terms of solar radiation to local meteorological file, okay, to be exported to this PV central. Okay, so it is based on one side on physical simulation. We work during 20 years on the modeling of BIPV. I show you several examples of different facades, semi-transparent, opaque, with color, not color, density of cells that can vary. So it is the kernel of the software, okay? It's able to model a lot of variety of integrated PV central and data analysis for a time in order to to learn about the behavior of the PV central and to adjust some parameters to the physical model. So after 2 or 3 weeks of running, the tools should be able to follow exactly the PV performance. Okay, it is the principle. And then, if there is a problem, so as soon as they start to have a discrepancy, okay, that means that maybe there is a small problem that has to be identified. Okay, so it's quite well placed compared to concurrents, to similar tools. And at that time, it's quite random. I don't know if you have seen that I show you carpet plot one day on a facade. We are using a lot of that carpet plot to treat the data, because sometimes if the inverter is not able to focus on the maximum power, they will have lack of data, okay? But that don't mean that there is a problem. Maybe there is something about the inverter, but so we are also obliged to first also filter the data in order to not identify errors that do not exist, okay? So it is this kind of carpet plot. I show you this kind of carpet plot for showing per day in the facade all the different level of temperature. One line was the temperature during the day. Okay, so I just finished the introduction. At the beginning of the creation, we were three, okay? So two co-inverters, me and Léon Gaillard, that is a research engineer that was working with me during 15 years. Okay, now he's in the startup, he's a CTO. And the CEO is an investor that believe in the products, and now he's a president of the startup. So we were three at the beginning for the creation. And now the startup has around 10 people working. Okay, so developer, informatic developer for the interface, data analyst, communication. Now there is commercial. Okay, it's so if you want to go and see what it's doing, if you see some opportunity, there is a contact here. Okay, so the principle is physical model, data analysis, and to see if there's match or if there's no match, what could be the possible problem. Question regarding this? If not, we can proceed to see on a real PV central. So it is on my campus, okay? You see here, the PV panels are here, are used to protect from the sun during summertime, okay? I give the latitude, 45 degree north, longitude, 5 degree east, okay? You all the time useful to know that. So a brise soleil is a shadow, okay? It's a cut the sun. And so there are 44 photowatt modules, okay? The reference are 1200 the model. The watt peak is 115. The inverter, there is also the branch, okay? And I give you the characteristic, okay, of one module and the inverter, okay? So I give you some question. In principle, you should be able to answer. So regarding the specificity of module and the inverters, what is the PV module's power loss coefficient as function of temperature? And what is the average efficiency of the chosen inverter? Okay? So I'll leave you think about. So you have to read the characteristic. You know? For the first question, so where you can find this Did you find that? Fine.
0.43%.
Yes. Good answer. So it is here. The power. Of course, there is an impact on intensity, voltage, but here the question it was about the power. Okay, so the coefficient is minus. So that means that you are losing loss of 0. Of the power per each degrees over 25 degrees. Huh? It is established here for 1000 watt per square meter, 25 degree, mass, atmosphere mass 1.5. So this coefficient means that if you are at 26 degrees, you will lose 0.43% of your power, expected power. Okay. Then regarding the inverter, what you can see that there is the same branch but with different range of inverter. Okay, so which one we will choose? What is important? I was. The power of it is this power peak.
So 115.
Yes.
Inverter power has to be more than this. Inverter in input power.
Yes. So what should be the input power? (44) multiplied by this, okay? 44 modules. So I find 5 Okay. So which inverter we will take? I said it is important to be in the good range because if we are below, you will not be able to follow the true track, the maximum power. If we are over, it's less important, but the accuracy will not be so good, so we will lose some energy. So which one we will take? Yes, this one. Okay, the range is between 3,500 and 5,500. So for this one, we saw that the answer to the question is 83.5. Okay, it is this. So it's a good, huh? The efficiency of an inverter, hopefully, hopefully is not bad. Okay, if you compute 115 multiplied by 44, you will find the power peak of your central that will give you the range to choose for the inverter. Okay. So this okay. Now we are looking that we never look before. Before we were just telling the radiation for 1 month is like this. What is the global irradiation potential production for the month? So we are thinking in months, in year. Now it's at time t. Okay, at time t, we look at the inverter and it will provide us some information. Okay, about tension, about voltage, about current. Okay, so here we are at time t. So at time t, the irradiation which is coming on my plane, okay, which is measured. How it is measured? Generally, it is a PV cell. Each PV central, they are not using a pyranometer. They are using a very well-known small PV cell. So with this very well-known small PV cells, we know exactly the temperature, and thus regarding the production of this well-known PV cells, we know the temperature and the radiation. Okay. So usually it's a small PV small PV cell which is put here and provide this. Okay. So at time t, we see that there is a radiation on the same plane as the module of 843 watts per square meters. We measure that the direct current voltage, so direct current voltage, so continuous, is 253, and the intensity is 14.7 ampere. Okay. On the grid side, so after the inverter, it's before and after the inverter. So you are now alternative. After the inverter, the role of inverter is to convert direct current to alternative. Okay. So we measure 231 volt and intensity of 15.1. The module temperature is at 55. It is still provided by both this reference cell that gives the temperature and the radiation. We assume that, and it is the case generally, that the connecting cable, okay, there is loss by Joule effect, and that this loss is around 1% of the power. If we find that it's more, that there is a problem. I will show you how we can see that it is more or less, okay? But generally it's around 1%.
This includes both AC and DC, right?
Hmm?
This 1% includes both DC and AC, right?
Yes, yes, yes. The global power loss. The global power loss of your system. So it's one part. At the beginning, you should estimate optimal power. and due to cable, you will lose 1% of this power at least due to the cable connection. Okay, we will see what is beginning expected power, and then all the loss that we are having. Okay.
So from module to inverter, it is DC cable.
Yes.
Then from inverter to grid, it is AC cable.
Yes. So it's
both.
considering both. Yes,
Both.
you're right. So okay. So I ask you to compute the efficiency of the inverter. Okay. We have the value provided by the manufacturer. The value is 93.5. Is it consistent with the value we are really measuring? Okay, this is real value. Huh? What I'm giving to you, it was real value. One day, it was in July, I don't remember. We have this radiation, this temperature of the cell is not ambient temperature, it's cell temperature. And this is the data provided by the PV central. Okay, so it's real value.
What's the ambient temperature?
Don't know if we have the ambient temperature here. It should be around 30 degree. 30 degree will provide
Maybe 25 we can consider. 25 we can consider.
No. We can't consider 25 because we will see that there is an effect due to the temperature, of course. I don't know if the no, not the temperature of ambience. But depending of the temperature of the cell, look at the lecture, we are able to come back to the ambient temperature due to what is called not NOCT. Allow to go to from ambient temperature to TC, okay? Or if you have TC, you can also evaluate the ambient temperature.
One range is given, minus 20 to 50 degrees. One range is given here on inverter reference table. Ambient temperature range is given.
Ah, it's given? Okay.
Minus 20 to 50.
Ah, yes, okay. Yes, but it is the operating temperature of the inverter. It will be. It is the reason why is that in very hot country, this kind of components are put in a cooled chamber. Okay, in the desert, for example, if you are you will put that in a room. If you don't cool this room, it could be over 50, so it will not work very well. So unfortunately, you are obliged to cool this chamber where you put the inverter, the battery. It's better for lifetime of these components. Okay. So usually, yes, in very hot countries, they are put it in a small house, in a small chamber, which is cooled. So part of energy which is produced by the PV central is used to cool the electronic device. Okay. So did you compute that? What I have to do? So I can call that efficiency of inverter. But you have to make the ratio between what you have before and what you have after. Between what you have after and divided by what you have before. Okay, you have the inverter, something is going in, something is going out, and you are losing in between. Okay, so what is going out is U A C E A AC. Okay, alternative, and then what is going in is U DC I DC. So it is 201 multiply 15.1 divided by 253 multiply 14.7, and here we found 0.937. That means 83.7%. The manufacturer was providing 93.5. So it's consistent, okay? There is no surprise. We can trust in the manufacturer. But it's good to check, okay? We are able, in each PV central, you are able to check because the inverter is providing this value, measuring it permanently what arrive, what is going out. So at a certain time you can check it. So now calculate the loss due to the rise in temperature of the PV modules. Okay. If we have not, here I give a short cut regarding the temperature because I directly give you the cell temperature. Okay. But if you have not the cell temperature, you can use the NOC correlation, okay, that will give you an estimation of the T cell temperature regarding ambient temperature, okay. So, can you give me the loss in percent due to the elevation of temperature? Elevation of temperature compared to what? To 25 degrees, okay? Due to rise in temperature, compare to 25 degrees. Instead of 25 degrees, we have Tc is equal to 50 something. 50? What I give you? What was the temperature I give to you? 50, no? 55?
Operating temperature.
For the cell temperature? 55. Okay, that means that instead of 25 degrees, which is Tc in standard, configuration, we have 55. So we have 30 degrees of difference. So it is 30 multiply okay And here we find minus. So we will lose, as we are losing 0.43 per degree, we have 30 degree of difference. We will lose at that time, precise time, 12.9%, 13% of the power. Okay, you see that you can feel the importance of the temperature. What is the theoretical power that should be produced by my central?
After considering this,
Hmm?
after considering this,
No. Now just compute some indicators, some metrics that are interesting for my operating condition. But now I start without any consideration what I should expect from my PV central. Here?
This theoretical efficiency.
Ah, no, not theoretical. This is the theoretical power.
This is 50601.
Hmm?
50601.
No, no, 506 kilowatt is power,
By the PV.
yes, but under 1000 watt per square meter. We have 506 kilowatt if I have 1000 watt per square meter. But we have 830. Okay? So what is here? The power. The power is theoretical because I have not 1000, I have 800, and so the theoretical power is, I make a cross product, okay? This multiplied by this, and this multiplied by this. So multiply by, okay,
265.
divided by 1000. Yes, yes, it is so 4, 2, 6, 5. Kilowatt. So it is P. Okay. So this is just related to the solar radiation. Okay. If I was at 1000 watt per square meter, regarding my the power, that will be 5.06 kilowatt, without considering the effect of temperature. Okay, so we are not at 1000, so it's lower, but the theoretical should be that. But of course, if we consider the temperature effect, it's not the case. We will have P2. Okay. So can you give me P2, PE2?
4480. 4480.
No.
Less
less. I have 3 dot something.
0.26 into 0.129.
You have to, compared to that, you have to consider that there is minus 12.9% of power.
3.71.
Yes. Okay, here it's without considering the temperature. Now, I'm considering the temperature effect and I see that the power will lose 12.9, okay? So P2 is equal to P1. So it is j'en suis okay. So while considering both that I am not at 1000 watt per square meter and I'm not at 25 degree. Okay. Now I ask you what is the power. So this is considering both radiation and temperature, which are not standard condition. Not at 1000, not at 25 degree. Okay. Now I told that I want to consider that there is around 1% of loss due to cable. Okay. So of course it will decrease again to consider that. So it will be PE2 multiply by 1, 0. Yes, is it? So you will find 3.677 kilowatt. Okay. Now it's not finished because we have to consider the efficiency of the inverter. Okay. We see that it is not at 25 degree. It is not at 1000 watt per square meter. There is loss due to cable. There is loss due to inverter. Hmm?
Inverter efficiency 93.5%.
Mm. So what do you find for P3, P4?
3.437.
I find 3.445. In principle, we should have the same result. Huh? I take the right. I took that. Yes. P4 is equal to P3 So we find 3.445 kilowatt. Is there some mean to check I have no committed some error in my computation? There is one mean to check that there is no error in my computation. Or it could be error in my computation, or it could be that, for example, the cables are not generating 1% of loss, but maybe more. Okay. I give you an assumption about 1% of loss due to cable, but there is one mean to check if this assumption is good or there is a problem. Okay. So what is this way to check? To compute another power, which is PE5. Which is the power after the inverter. I'm able to compute this power after the inverter. What is the value of this power? Depending of the measures that I have made. It is the power that I can extract from the measure of the voltage and intensity after the inverter. So 231 and okay. And in principle, I should not be far from this while considering all the loss, including the inverter. Okay. So here, if I compute that, I found 3 dot. So you see, it's not so far. That means that my assumption about loss in the cable is not so bad. If I was far, it's a mean to check that this may be a problem. Okay? So when I was representing velocity, it is one of the things that it is constantly check. Okay, power which is extracted from the data after the inverter and considering all the loss. Okay, and if there is a discrepancy, that means that maybe one cable is cut or one cable is overheating because there's too much Joule effect or thing like this. Okay, it's a way to check if it is full consistent. The fact that we have not 1000 radiation but 843, so the power is lower, is not a problem, it's consistent. The problem that we consider the temperature and the power is low, it's consistent, okay? The cable that we estimate at 1% in loss, this is a way to check that the assumption is not so bad. Okay, the cable seems to be okay. We are not far. Maybe 1% is too much, because here you can see the power that we identify while considering all the is a bit lower than the real one. This is the real one. So that means that probably the loss of the power in my cable is less than 1%. So it's better like this. Okay, it's a mean to check. So P4 and P5 are quite very similar, so that means that the installation seems to work fully good, in a good condition, okay? Now we will compute the performance ratio. So what is the performance ratio? This is, I forgot, there was a 5 here. So how can I compute the performance ratio? So it is to have a global evaluation of the performance of my PV central. Okay? So, of course, it is a ratio between two power, which one divided by each one. Hmm? But it is what I can expect. It is the maximum. So the maximum will be here. That's what I have in reality. In reality, I have that. Real divided by what I can expect. So it's P5 divided by P1. So can you give me this? And tell me if it's well or not. Um?
81.0.
Yes. So yes, you're right. So I have 0.117. So it's over 0.8. I say that if it is at 0.8 or over, it's very good. My PV central is operating in good condition, no problem. If it is lower than 0.8, maybe it is too hot because it's integrating in a building, so it could be 0.75, maybe zero other thing, soiling, okay. So this is over the 0.8, it's okay. So PR is an efficiency, okay? Another way to compute PR, it is, you know, when you have a lot of different efficiency, what is the final efficiency? You know, I know 80%, then after I have something, 10%, then I have something, what is the final global efficiency? It is a multiplication of all this efficiency, okay? It is N1 multiplied by N2 multiplied by when there is many efficiency following, okay? So it's another way to compute it. So try to compute considering each efficiency at each step, okay? And in principle, you should not be far from here. It's also a way to check that we don't make a mistake. So you see how to do. First, you have the temperature effect. So it was 1 minus efficiency linked to temperature effect. Then you have cable loss. It is 1 minus, we said 0.1%, okay? And finally, you have the inverter, okay? Okay, so two ways to compute. What I have finally as a power, what I can expect. Or the other thing is when you have a kind of cascade of transformation with each time an efficiency, the final efficiency is a multiplication of all the efficiency. Okay, so this effect of temperature, cable, inverter, and in principle you should not be far from this. And if I do that, I will find 0.807. Okay, so compared to that, it is very close. Why it is not exactly? Because I told you previously that there is chance that my loss due to cable is under 1%. So yeah, I find more because in reality, the assumption that I've made that 1% of power was lost in the cable is not really true. It's a bit lower, which is better. Okay. Whereas here it's considering all my efficiency and this assumption here that it is 1%, but in reality it should be less than 1%. I can exactly identify this percentage compared to that. Okay? If I say that is equal to 0.817, what is this value here? I will find, for example, 0.007, so 0.7%, okay? To find the exact value of the, and that will give me an estimation of the exact loss due to cable. It's a way also to analyze that. Is it clear? Okay. So it is the performance ratio. I should have given some other question after. Can I change? Okay, well done. Now, given the sun exposed surface, so we have 44 PV panels for a surface of 45, so it's almost 1 square meter per panels. What is the theoretical conversion efficiency of the generator at 1000 watt per square meter at 25 degrees? So do we have an idea of the range that we should find? So PV conversion of my PV central finally. Could be around up to 10 to 20, depending on the technology.
11.24.
Yes. So in theory, I should produce what arrive on my panel. It's 45. Sorry. Yes, it's yes. Okay. Theoretically, what arrive on my panels in standard condition. And so the efficiency of my PV central it is what I can expect theoretically. So with my power, I can expect that. And compared to what is arriving, Okay, so we find 0.112. Okay. So that means that 88 only one. So 88.8 are lost. They are coming, they are collected, but not converted. Okay. Okay. So now we have this per month, so it's more what we used to exploit till now. Okay. So January, February, March, all the, and this is the year scale. Okay. We noticed that the electrical production in January was 227. We ask you to compute the performance ratio for each month. Okay. And to identify when is the minimum, when is the maximum. Check that. So can you complete that?
January is this 9.5
For the first one?
9.5.
No, I have 0.84. Zero. accumulate on the year. You find?
Yeah, but area considered to calculate
Hmm?
area considered to calculate
How to 27 by 53, 4.3.
4.3.
Area will be 4.3 square meter, right?
The area of the solar PV, it's 45.
53 multiplied by 445.
Mm-hmm.
E divided by 55 times area
Mm-hmm.
will be 9.5%.
Mm. Did you consider the efficiency of the conversion?
That's efficiency.
Because not all should be converted. I have not the detail of my computation. Somebody find this value. Somebody else find?
Yes, sir.
You can come for one demonstration.
Yeah, we got it.
If you find it. You go for one for the first value. So for January, so can you explain what you
This is the solar radiation in 1 month.
Incident radiation.
Yeah.
Mhm.
Then this is the area,
Yes.
and this is the efficiency of solar panel. So that 268. 268. Point. About 268 we get.
Mhm.
And then we divide it 2 to 7 divided here. 27.
Divided by how much?
268. That one. So performance ratio will be 0.847.
4, 7, yes, okay. Mhm. Okay, thank you. So it's a way to evaluate, yes. In principle, we should have that, okay, but we don't have that. So the difference is due to the performance ratio for PV central. And so it's like this that we estimate the performance ratio per month. Okay. Otherwise, it's not easy to see if in July it operates well or not, because the sun radiation is all the time different. So we don't know if that is consistent with that is consistent with that, because looking like this, the irradiation is all the time different. So we have to consider something common, okay? So what we can see from that is that we are producing more, okay? We are producing more during summertime, much more. Okay, you see here, 726 kilowatt hour during July month. So we are producing much more than in January, but the PV central operate in a bad condition compared to the winter time. Okay, we're producing much more, but the performance ratio is less good than in winter time. Okay. Why it's less good? Because of temperature. Temperature is higher. Okay. So we can see that a PV central will produce more in sun day because the days are longer and there is more sun, but the performance is less globally because here the temperature could be also linked to the soiling or thing like this. Okay, so it's this performance ratio is interesting, very interesting to see if the PV central is operate or not in good condition. Okay, so the performance ratio on the whole year could be on the year is equal to 6,305 kilowatt hour divided by what is coming. What could be expected, and this is 0, not 1. Global electrical production, electrical annual electrical production energy for a year is equal of 6 kilowatt hour. Okay, it is that. How many hours per year the PV central is operating in the power peak condition? So it is the total of the production divided by the power peak of my central, and it will provide 1,206 hours. It looks like if my PV central was operating during 1,246 hours at my power peak. It's not really the case, but just to have an equivalent, how many hours per year I can consider it will operate in a maximum power factor. Okay? Do you have any question?
What is the actual formula for the performance ratio? Means, it is sometimes mistakenly can be write as efficiency, and sometimes it is different. That's why.
No, you have two kinds of efficiency. You have the efficiency of your PV panel. Okay? So this is independent of the performance ratio. You have a certain amount of solar energy coming on your PV central, and you know that only 12, 15, 16% will be converted in electricity. It is efficiency of conversion. Okay? But the performance ratio is the efficiency of the global PV central. Okay? So that we don't consider the efficiency of the conversion finally, because it's already known that we will not have more than 15% because of this panel. Okay, so it's not a problem. It is linked to the panel, which is not able to convert more than 15%. Then, starting from this, we look at all the stage where we could have this power, but we have not this power until the injection on the grid. Okay, and it is this whole chain that considers the performance ratio. Okay, the performance ratio don't consider the efficiency of the performance of my panel. It is done like this. It is a cell like this. You are buying a panel, you have an efficiency. Okay. So you can't increase that except if you change your panel. Okay. So the performance ratio is when it is integrated, what you should expect and what you are really at the end. Okay. So this is the performance ratio. It is the efficiency of my PV system. Okay. And it's different that the efficiency of my PV panels, because when I buy these PV panels, I know that limitation.
You can actually control this part.
Yes, it's normal. The conversion, photo conversion efficiency linked to a PV panel is normal. It's cell like this. You can't change it. But what you can't change is that there is a problem on your PV central. Cables that are inducing more than 1% of loss, soiling that you will decrease. You are expecting that for such a sun, you should have this, but you don't have it. But maybe there is soiling that reduce incident radiation and things. So the performance ratio is characterizing the operating condition of your PV central, if it is well or not. Okay, and it is important that it's good if it is over 0.8. 80% is good, so no problem. You don't have to check every day. If you find that it's good. If it is below, you should investigate the reason why. Typically here it is below, but we know that because the temperature is probably high. Okay. But if it is winter and you find that in winter, a problem. It could be snow on you that generates shadow on your PV. Okay, so you are, or it could be something wrong with one PV panel that is destroyed. Or okay, this in winter is not normal. Yes, or because the installation is not well integrated. So put on the insulation and it should be working better than that, and it is not the case. Okay. So it's a matrix in order to give you information of the well-being of the PV central. It's important. Okay. Because like this, if you just look at this, you say, oh wait, yes, I'm producing a lot, but you don't know if you can produce more or it is less than expected. So it's a very interesting matrix. Okay. Other question? So if you have no more question, we can conclude here. So I just want to tell you that I was very happy to spend 1 week with you. And I hope you are interested by the lecture and tutorial that we have done. And this target, the aim of this was to give you an overview of all the solar technology, to give you idea of some range of power that could be expected, range of temperature, how we can identify if a performance is okay or not, what the range of performance also for regarding the use that you need after different technology. So it was quite dense, but I hope that you have learned things and it was interesting for you. Thank you.
So it's a very interesting session, right? So everyone participated, and now you know how to investigate the performance of a solar PV power plant. Okay, how this temperature plays an important role. Even though we think that in summer it will work best, but not. It's winter. But at the same time, we need to check if this cloud cover and then maybe what is called snow is covering.
Yes.
Then again, we will not get that much of radiation. That is also important. Okay. So thank you for your presence, and please come at 2:30 sharp. We'll start today, not 3 o'clock. It's 2:30. So you have to quickly take the lunch and come back. Right? Okay, then see you at 2:30. Thank you. It is very tight. Just 2:30. We have to come back here.
Ah yes, what time is it? What time is it now? I didn't check.
202.
Ah, okay. So who buys this? Because I can refer. So it's 3,000.
So, welcome to the post lunch session of day 5. So, we will be starting this tutorial number 7. So, it is estimation of drying kinetics and energy consumption of agricultural products. That is one problem, and maybe another problem we will solve. So, problem goes something like this. You can consider total mass of grapes is about 100 kg, and the initial moisture content is 75%, and final moisture content is 14%, and drying time is 2.8 hours, and maximum allowed temperature is 70 degrees Celsius, and ambient temperature is about 25 degrees Celsius. Okay. So, how to proceed with this problem? So, what are the parameters? T M I M F is known to you, and then you have maximum allowed temperature and ambient temperature is known to us. Then what could be the water removal based on the wet material moisture content. So, we can find out W in minus W out divided by 100 minus W out. Okay. And then if you substitute these values, then it is it should be moisture content is like 74 we have considered, but it is it should be 74 actually. Then it will be this is 74. Then your W will be 0.71 kg per kg of material, right. Then for 100 kg of product, water that has to be removed is how much? This is 0.71 kg per kg of material for 100 kgs. You multiply with 100, then it will be 71 kg, right. And the amount of material dry in 2.8 hours. So, it will be like 100 kgs, and time is 2.8 hours, right. So, it will be 35.71 kg per hour, right. So, how to find out this drying rate? Yeah, see drying rate you can find out by using this 35.7, okay, 71, and then you have 0.71 is the kg. So, it will be 25.35 kg per hour, right. So, we need to use a enthalpy humidity diagram. So, it's a long you need to find out what could be the relative humidity at this condition. So, that chart is available, you can just browse it. For your convenience, I have given these values here. So, for air at 25 degrees C and relative humidity 60%, absolute humidity is 12 gram per kg, and enthalpy is 56 kilojoule per kg. Okay. And for air at 70 degree, relative humidity is about 6.5%, and enthalpy is about 100 kg per kilojoule per kg. Okay. So, we can get a average humidity is about 78.5, and for mean air humidity, which is 78.5%, the air humidity at the exit of the dryer is about 28 gram per kg. Okay. and from that chart actually we can find out the corresponding temperature is 35. So, there is a chart. So, we can use that chart with this condition and we can find out what is the temperature at the exit of the dryer. Okay. So, then we need to find out the air needed for drying of 100 kg of raw material. How much air is required for drying of 100 kg of raw material. So, we know MW and then density of air and then XM minus XA. So, how did you get this 28 minus 12? Can someone tell me from where we got these values? 28 minus 12. What is XM and what is XA? Yes. So, this is 28 gram per kg. This is humidity. Sorry. So, exit of the dryer, how much is the dryness, right? And here we have 12 kg. This is absolute humidity. Okay. So, that is 28 minus 12, and from there you can find out what is the air flow. And once you know this, then you can find out the heat needed to increase the drying air temperature from 25 to 70 degrees Celsius. Okay. So, for this we need this enthalpies. So, already you know how this can be studied from a psychometric chart, what you have studied in the last class also, because we need to use the psychometric chart. From there we can find out. I have the chart, but I am just cutting short because already you are aware how to calculate it. Okay. So, what really we need about the Q value, which is the heat needed to increase drying air temperature from 25 to 70 degrees Celsius. Okay. So, once you know enthalpies and already you know density of air, and then you can find out the amount of energy required. So, these two are at the two different enthalpies, because the enthalpies are functions of temperature, right. Then for about, if we say 2.8 hours of drying period, how much energy consumption would be? So, that can be very easily calculated. So, this is for 1 hour, this is for 2.8 hours, or maybe if we extend for 3 hours, that is also possible, 4 hours is also possible, right. So, next maybe what we can calculate is energy consumption is about 19.52, and then this collector area required may be calculated from the heat required over amount, which is 19.52 for that temperature range, by taking into consideration the solar collector efficiency and corresponding heat losses. Okay. So, once you are confirmed that this much of heat is required, then you can actually do the back calculation. So, if this is the amount of energy you require QU, then you see the amount of losses will take place. Okay. So, that way you can do the back calculation, and then you can suggest what could be the total energy required. That means, this plus UL will be the amount of energy received by the collector, right. So, if you add the losses with this value what you have calculated, right. So, that is how we can do the calculation. So, for this we need this enthalpy chart as well as psychometric chart. So, already you know the psychometric chart, right. At different conditions you can find out, once you know the drying from say this temperature to maybe 45 degree temperature, then what is the specific humidity? It is 28 and 14. Okay, so this is the humidity range. So you can use this chart and you can find out the enthalpies. These are the enthalpies, right? So you can find out the enthalpies, and once you know these enthalpies, then you can find out the heat required, right? So these charts are used in extensive. I think you have used this chart for while doing this psychrometric analysis, but see, this chart can be used in many applications, right? So yesterday we saw one applications, and today also we saw one applications of using this chart for heat requirement for carrying out a task. Okay, so temperature change is known, relative humidity is known, and enthalpies are known. So from that you can find out change in what is called heat required for doing that particular task. Done? It's fine. So now let us solve this problem. Let us spend some more time in this figure. Okay. So here this temperature rise delta T of air through a vertical south facing unglazed transferred collector. Okay. So this is no collector, and then as you have seen in the class of Professor Christophe, so this is goes, and maybe this kind of fans are there, and then there will be ducts here, and then there will be ducts here, and something like this. Okay. So this is the wall. Okay. And air goes something like this. So what it says, and it is south facing. It is south facing. Okay. And this is unglazed transfer collector. No glazing is there, right? And this actually the kind of collector satisfies this expression delta T is 0.03 IT plus 3.0. Okay. So for an airflow rate of 36 cubic meter per hour per meter square of UTC, that means mass flow rate per meter square. Okay. And IT for solar radiation is given to you is how much? Is the global radiation is given, and then diffuse radiation is given, and you need to find out the total radiation on the UTC, and also we need to find out the efficiency of the system by using this data. Location is given to you, then depth, hour angle, airflow is given to you, then global solar radiation and diffuse radiations are given to you, and of course relative humidity, reflectivity of the surrounding surfaces is 0.2. Normally we consider 0.2 in most of the calculations. Okay. So can you start it? Can you start? So this is IG, and this is your ID. Okay. And this reflectivity is rho. Rho is given to you as 0.2. Okay. Fine. Then the expression for IT, and from this value we can also find out what is beam radiation falling on the collector system. It is IG minus ID. So IG is 543 minus 144. Okay. So you can find out what is this value. Can someone tell me? 199. It will be 399. Yeah. this is in watt per meter square. Okay. And probably I need to find out this IT is IB, RB, ID, RD, okay. So, what is RB, what is RD, what is RR, this also no expressed. Okay. So, what is RR is still factor, right. So, this is RB is cos theta by cos of theta z. Okay. So, what is cos theta? Any beta is given here. Beta is of course 90 degree here, it is 90 degrees vertical. Okay. So, beta is 90 degree. Okay. So, what is the expression? Sin delta sin of phi, beta is also there somewhere. No, here you have beta will also be there, right? Here tell me what is this value, sin delta, sin phi, then plus cos of phi, cos of delta, cos of omega. Then it is phi minus cos of phi minus beta, cos of delta, cos of omega. You remember this? So, now for this you need delta and phi, beta is 90 degree is known. How to find out delta? 23.45 sin of 360 by 365 284 plus n. So, now n is for December 10. So, you can find out what is n. So, n will be, so 365 minus 21 also you can do, or you can add also. Okay. So, for your understanding what you should do, so it is like 31, 28, then 31, January, February, March, then April, May, June, July, August, September, October, November, then 10. Add this and calculate what n you will get. Otherwise, what you do, 365 minus 21 is also possible. Then can you tell me what is phi? Phi. Oh. And already you know what happens in equinox days and solstice. So, that will give you information. So, what could be the values of delta? So you don't have to do so precise calculation actually, no, sometimes you can find out. What is delta? Zero 4, right? 0.49. Okay. So now what is phi? Phi is from here you can find out. Then phi will be 28 plus 35 by 60. What is this value? Phi is 28.583. So latitude is known, then tilt angle is known, then delta is known, beta is known. We can find out what is RB. We can find out what is RB. RB we can find out. Because first we need to find out this total radiation incident on UTC. So that means IT. IT you need to find out. Can someone tell me what is RB? RB how much you got? Do the calculation, then you know you will get it. I think you should get something like in my calculations I got it about 1.295. You can cross verify. Okay. Got it. So, what is you have R d 1 plus cos of beta is view vector with respect to the sky, right, and R d will be something like rho is the reflectivity, then 1 minus cos of beta by 2. Okay. So, what are the values of R b, R d and R r? This is the view vector with respect to the ground. Okay. So, for reflected surfaces like when your place is covered by snows, then this point will be very crucial. Okay. Point 5 and here 1 because cos beta is what is 0, right? It's 0.1, it is 0.2, it is 0.1, right? Okay. So, now you substitute these values here in IT and then you see what is the value you get. So, I will just rub this part. Now, these are not required, already you have used those values. Yeah. So, IB is 399, right? 1.295 plus ID is how much? Diffuse is 144, right? 144, then we have RD, this is RR, right? RD is 0.5 and then this is nothing but IG and this IG is 543 multiplied by 2.1. So, now you can tell me what is this value. Okay. So, these are not required now. What is IT now? 641. So, we have done with this total radiation incident on the UTC is 641 watt per meter square. Okay. So, beam radiation is 399, then diffuse is 144 and hence global is 543, but no, actually total radiation falling on the collector is 641 watt per meter square. Okay. So, it is higher, right. So, now what you need to calculate? Efficiency of the collector. So, how do we calculate this efficiency? Efficiency of the collector. So, how are you calculating this efficiency? What values are given to you? Useful heat gain. So, QU IT now. So, this IT total IT you need to use, and then we have A is the area of the UTC. So, what is the area value here? Okay, area is given, is hidden area. Okay, area is given. So, QU is MCPDT. Okay, QU is M dot Cp then dt. Okay. So, dt has to obey this, and then you have IT then A, but see what is given to us is 36 cubic meter per hour. Okay. So, that means this 36 cubic meter per hour meter square. So, if we multiply with density of air, okay, then what will happen, and its unit is kg per cubic meter. So, this will goes off, then what you will get kg. So, density of air is maybe you can consider 1.2. Okay. So, 36 into 1.2 then kg hour meter square. That means you can use this 36 into 1.2, and Cp of air is 1005 you can consider, or maybe 007, 1005. Okay. Then you will have IT is 641. So, this A is taken care by this expression, right? This A, right. So, this A is taken care by, because this is meter square, and this is 1005 and delta T. So, delta T is how much? Is a function of IT. Okay. So, I will just rub this part, this is this part. Okay. Then delta T is how much? Can someone tell me? Is IT is 641 plus 3? How much? 22 T3 degree Celsius, right? You substitute here in delta, this delta, that 1005 into 22.23. That means if I expand this, is 36 into 1.2, 1005 into 22.23 divided by 64, 641. Now, tell me what is the collector efficiency now? But you got RB 1.295, right? Omega you have considered 15, right? So, what is efficiency of the collector? 40. Huh? Yeah, 3600 you have to divide, yes. It's a unit conversion, right? So, because this is in kilojoule per second, so this will be 3600. So, finally, this will be 41 point. It's quite interesting problem, right? Just we gave some input parameters. It's a solar air heater. We gave some amount of volume flow rate per square meter, and then we have actually included all the analysis. That's why I have picked this example. So now just recalling the expression, what is RB, okay, and what is RD, what is RR, and why these expressions has come into considerations. Because we know normal radiation, we know diffuse radiations, also we know what is the total radiation falling on the collector. Okay. So that expression also we know, and individual calculations also we know. So from that we can find out if there is a expression which tells about delta t that can be expressed, okay, and of course it is justified, and also we know the expression for collection efficiency. So we can characterize the collector also, okay. So all the informations are here. So it is quite interesting, and these raw values will change if we consider a place like full of ice. So reflectivity will be different, right? So this is like a radiation shape factor with respect to the ground. So when we are calculating RR, it is radiation shape factor with respect to the ground, and but RD, it is the radiation shape factor with respect to the sky. Okay. So that's how sometimes this reflected radiation plays a very important role in the overall performance of the collector system. Okay. So it's good, and also we'll solve one more problem quickly, and then maybe we can little bit early you can start the exam. Okay. Fine. Okay. One more very interesting problem. Okay. Now we have to solve. I am not going to solve anything. So you can help now. So a water heating flat plate collector is fitted with two glass covers and a non-selective absorber plate. So no selective plate is there, and the dimension is given, and the collector is tested under standard procedure, and following data are generated. So you know TFI, TFO, then TA, IT, all these values are given. Okay. And also tau alpha average, then mass flow rate, then CP, and then AC to AP is given to you. We need to calculate instantaneous efficiency and plot this against the parameter TFI minus TA, and draw a base straight line, base fit straight line, and determine the values of UL and FR. Okay. How does the values of FR changes if the values of mass flow rate is reduced? So mass flow rate I am going to reduce it, because see this is what flat plate collector, and we are dealing with water. In the earlier example we were dealing with air, right? So this is for water. So now we are increasing or decreasing the mass flow rate. That we would like to see what happens if we do something like that. Okay. And for assume the value of this does not change significantly because of the increase in mass flow rate. So this same FDS we can use for both the cases. So can you do it? Everyone is having a laptop, right? And also internet access. No? Then how will you write the exam? You need laptop. Mobile is also okay if you have Gmail account. Gmail? Wi-Fi access नहीं? You can do something. There is no shortcut. Things are there. No network. Why you are saying network is not there? Let me check if I get something from there. Can you do it now? What will be the efficiency? You remember this? In the class we said in testing. So, two parameters we have considered, that is not T f bar, T f o minus T f I divided by I t, right. So, that you consider T f o is there, T f I is there, and divided by I t you do, and then you plot it, then you see what you will get. So, you will get this kind of plot. If you have a spreadsheet, like no computer and then a spreadsheet, immediately you can plot it. So, just I have no picked the things, that is why nothing is there in the x and y axis, and of course, this will be efficiency, and this is the other parameter T f o minus T f I divided by I t. So, that means you have this efficiency values. Then once you can once you draw it, this is T f I minus T a, sorry, T f I minus T a, then I t, and then you can find out what is U L and F R. So, actually you need this laptop here, it is very easy to do it. laptop ले ना एग्जाम एग्जाम नहीं देना है लैपटॉप लेके और ही तो कुछ नहीं होगा ग्रेड नहीं चाहिए ये तो गो फास्ट इसके पास तो कंप्यूटर नहीं है computer you are caring for fun, not for work. एक्सेल यहाँ पे कर सकते हैं
एक्सेल नहीं एक सर करके दिखा सकते हैं हम लोग
एक कहाँ है सब तो करना पड़ेगा
यही है क्या एग्जाम
एग्जाम नहीं है एग्जाम ये तो पूरा सुपर है so you can do it right okay fine So, okay, you can generate this kind of plot and you can calculate this way. So, area is given and then efficiency you can calculate, and then for first set you can do this, and then second set you can do this. So, you can do for all these things. Okay. So, by doing hand calculations you can plot it now. So, this will give you a lot of understanding. It is a very interesting problem. So, why I am choosing this problem, because if you sense the mass flow rate, nothing will happen actually. That is what you need to demonstrate. I think there is a mistake here. If you could figure it, it should be T A, right. So, if you see this T F I minus T A by T, at least you do the first calculation. So, what is T F I minus T A? So, this is 84.95 minus T A is how much? It is 23, right? 23. Then you have IT is this much, 885. What is this value? 0.07. And for this, just do it once again. -79 minus 23, minus 22.4, 79.97 minus 22.4, then 879. Tell me. 65. Why so variation? Then this minus this divided by this, how much?
0.062.
This is 0.
0.065.
Yeah. Then 69.54 minus 21.6. How much it is?
0.057.
Next, Akash. $68.19 minus 21.3 divided by 827.
0.056.
56. Then this and this one 43 minus 20.4, 7 divided by 792.
0.0292.
Then 38.17, and last part 33.29 minus 19, 761. What is the efficiency? Oh, again you need to do efficiency, right? This parameter is something like TFI Fi minus TA by IT. Okay. And what is the efficiency term? MCP TFO minus TFI I so what is delta T here? TFO minus TI. Can you tell me these two differences? This minus this 93.98 minus 84.95 02, right? So someone can do this calculation. So this part is done. So efficiency term you can do. So this A is how much? 2 square meter, right? 2 square meter, and then I is first case it is 885, and then M is 1.1, and this is 1.1. Then we have 60 at the bottom. Okay, and CP of water is 4.18. That means it is in kilo, and then you have to have this one, and then delta T. Minutes, that's why 60 is here. Okay, 60 is here, 885, 10, 2, and you can make one, like Excel sheet, and immediately you can tell actually this part, because this will be fixed for all. Okay, only variable will be this part, and of course I will be your variable. So what is the second delta T? Then third one? Then other people are sleeping or what? Only one guy is month. $61, 77.36 minus 68, 9.17, 11.14. Do it quickly. This is also 11 point something.
What is missing? 11.62 is for 38.16.
Oh, then here. Okay. So now you calculate this. So can someone tell me what is this value? 1.1, 4.18 into 10 raised to the power 3, and then a divided by a, and this part will be variable, right. So, if you multiply, that means 1.1, then 4.18, okay. Then you will have 60 into 2. So, this part will be fixed, and delta TFI will vary. So, this TFO minus TFI by I, this will be the variable. Okay. So, what is this value? 60 is for this minute. So, 1.1 divided by 60. This part? No, I will be varying. I will be varying for every cases. Okay. So, this part is fixed. So, what is the value of this part? This part, right? 38.31. 38.32, and then for every time this will vary. So, this is known divided by IT. So, that is why I said, no, if you have computed any very quickly you could have done it here. This 0.3.
Efficiency is 0.3.
0.3
Total efficiency
is
0.38, so 38%.
30
39.1.
for this case, first case,
First case.
39%. So, that means you can plot it. Oh, no. Oh, very good. Someone can come from top, then you can convert somewhere. Okay, very nice. Yeah, very nice. So, that is plot is also there. Then we can find out these values. Then we can find out these values UL and UR. So, that by using this curve fitting, we can find out what is mx plus c.
So now efficiency is calculated.
Efficiency, and then this other part like TFI minus TA.
Yeah, which is there.
Yeah, these two. So, this will be in the x axis and the y axis.
This one is
Yeah, this will fine. Yeah, this will be fine. So, fitting coefficient again. I think right click it, I will get it there.
there it's also.
Yeah, right click.
Here it is also.
Formula. Okay, should come.
Yeah, actually
Equations it will come.
it should come. See, I had to select everything together.
Equations.
Now it is coming, but here plus error bars.
No, third line.
After that here
Linear.
and more options we click and
Linear equations. So, equations.
so equation will be there.
Display equations also are score values. Yeah.
Let's make it big.
Yeah. So, now can you tell me the expression? So, this the I is equal to 0.6 minus 0.6 minus something will come. No, y is equal to mx plus c. That equation what we have discussed.
minus 3.5412x minus 3.5412x
541
2x
2.
2x
That x is something like TFI minus TA by I, right? And this is 0.6.
0.6466.
Okay. So what is this value now? And what is this value now? You remember?
Slope intercept
And this is intercept and then slope. So intercept was something like FR AC by AP tau alpha average. And this is equal to 0.6466, right? And then what is this value? Other values? So tau alpha is known, and then this is UL. This is what? UL AC by AP is 3.5. Okay. So now you can find out what are the values. It is quite interesting problem. So you know already EC by AP is 1.2, and tau alpha average is given to you. Okay. Now we can find out what is UL and what is FR. Okay. So now it's very easy, everything is known to you. So your FR and UL can be found out, right? Now next question is, if we change the mass flow rate to 1.3 kg per minute, then what will happen to the value of FR? So you can see, then you can tell me what happens. Then again you need to do this entire calculation. If you have computer, immediately you can do it. So in hand calculation it will be difficult. Just you change this parameter mass flow rate. So from 1.1 to 1.3, and once we could develop this expression y is equal to mx plus c, or here y is equal to minus mx plus c. Okay. So that if you can develop, then immediately you can find out what changes you will get, FR value. Not much change will be here. So what FR you got now?
FR is 0.97281.
Yeah, 0.7281. So FR is 0.7281.
So you want to change the
Mass flow rate
1.1
1.3.
1.3.
Yeah.
We have a new equation.
Yeah.
New equation is FR, right? So 0.7641.
Yeah. Control I'll just write there. So our new equation will be 0.7641 and 85. Okay. So now, if you could find out this FR, then what will happen? Because this is nothing but FR multiplied by AC by AP, then you have tau alpha average. So here I want FR, and how much That is significant change. We need to check somewhere. I made mistake, I think. There should not be so much of difference. Yeah, so we close. So that's how we can say that even though there is a change in mass flow, that there should not be much variation of these values. Okay. So it's an interesting problem. So this actually leads to one kind of design of flat plate collector. Okay, and you can extend this understanding for other collectors as well, where liquid is injected into the collector system. Okay. So, okay, finish it there. All right. Okay, please exercise this kind of problem, and it's fine. We can go on doing the exercise, but no, if you are concentrating in one exercise very precisely, I think other things also you can do it. So we have solved for drying, we have solved for solar air heater, and then we have solved for liquid flat plate collectors. So all the things we have touched, and we have given thoughts about it. So we can conclude here this session. Okay, and maybe for some time we can give a break. Okay. Then you can come little early. You can start. I think since all people are here, online, but we can explain. We can tell them. We can start little early. 4 o'clock will be good actually. Then we can do something at the end. Okay. Okay, then we'll break for half an hour, and then we'll start at 4:15. Please ready with your system, and it will be online test. Okay, and everything will be there in our system after exam is over. Then we could able to give the grades. Maybe for getting grade from academic section, it will take some time. But we'll complete our process today itself, and because his signature is also required there. Okay. So thank you very much for your presence, and maybe one more photograph we can take. Oli, what do you say? So photograph we can arrange one. I'm seeing you photograph. Okay. Okay. Thank you. So, good afternoon. I welcome you to the last session of the course, and this session is valedictory session. So, in this session we are going to distribute the certificates, and of course grade at this moment we will not disclose, and everything is set now. So, grade also ready, and you will get the physical grade later on. Maybe we will mail you, and you will get the card, and that is from IIT Guwahati get card. So, this has to go to academic section, and they will process it, and finally you will get the grade. Okay, once they approve it. So, before we distribute the certificates, we would like to hear from you, like how did you find this course? Was it interesting? And what you have learned, and then what new things we can include. So, that kind of feedback I want from you. Those who are interested to spend some time, they can tell us, and maybe I will start with someone who can raise your hand to speak something. Yes.
Very good evening to all present here. Let me introduce myself. I am Venkatesh, working as assistant professor in the Department of Mechanical Engineering. I am coming from Dr. Mahalingam College of Engineering Technology, Pollachi, Tamil Nadu. My sincere thanks to my college giving this opportunity with all supports, and then my special thanks to these course coordinators and the organizing team who is working in this background. I'm basically working, I'm doing research in parabolic stuff, solar collectors. I have learned all the recent topics and technologies in the solar technologies. And then, the program was well structured and properly organized, and I have learned more about solar collectors and then for my research work. The purpose for this course to gain knowledge and then I have fulfilled my objectives in this course. My heartfelt thanks to my resource person, especially Christophe sir. And then I'm the big fan of Pankaj Kalita sir. The food accommodation is very nice. Organizing team, they responded quietly to all the queries and the clarifications. Once again, I thank the organizing team. I'm in stage to complete my research work. If it's possible, I'm doing PDF under the guidance of user. Finally, all the best to all the participants. Thank you.
Thank you very much. For comments.
First of all, let me introduce myself. I am Dr. Hakim Nias. Completed PhD in IIT Guwahati only, Mechanical Engineering Department. Now currently working as Assistant Professor, Energy Institute, Bengaluru. It comes under Ministry of Petroleum and Natural Gas. First of all, I would like to thank the course coordinator, Dr. Pankaj Kalita sir, for providing me and all the people opportunity to attend this program. First of all, I want to say I am taking this course, Solar Thermal Systems, in my institute for MTech students for past 6 years. So after taking 6 years course, after much refinement also, I am able to learn many new things from this GIAN course. That is my first point. And the second point is I have attended, this is my 7th GIAN course, right from my PhD till now. And I can say that with confidence that this is the best GIAN course I have attended out of the 7. The reason being both Professor Ménézo, Christophe and Dr. Pankaj Kalita both explain the theory behind the thing, concepts, second the practical applications, and third especially the most important, the tutorial sessions. So all the three were well structured and well nicely delivered to all the students. So it was quite handy for all the participants to absorb the things. So, and once again I thank the organizing committee. They responded also very well. Accommodation is good, the stay is very comfortable for us. Thanks again.
Thank you very much. speak something. Is alumni now. You can speak.
Good evening, everyone. Myself, Hematologic Medics. I'm coming from Minister of Engineering College, Kokrajhar, and I am coming along with my 5 students. Please stand up. Okay. So I'm coming with my students, 5 students. We are from Chemical Engineering Department. And we attended Pankaj sir's. Actually, I would like to thank on behalf of our Minister of Engineering College, Pankaj sir, his organizing committee, Professor Christophe sir, for giving us such a knowledge, delivering lectures. Actually, I'm not so much good in speaking, but thanks to all and everyone. Thank you.
So first of all, very good evening to everyone. I would like to thanks Center of Education Technology and School of Energy Science and Engineering for organizing such a fruitful event, and especially Professor Christophe and Professor Kalita for sharing their views on solar technologies. In our BTech course, we have a subject called Alternative Energy Resources, and there we have learned a glimpse of this solar technology. But in this course, I think my friends and I have learned so much, and more than the course we have studied in 4 months. So thank you for organizing such a beautiful course, and I would like to request sir to organize more such beautiful courses in future, and allow us to participate in that. So that's all I have to say. Thank you.
Thank you. Very good. Alumni now.
Good evening, everyone. I am Abhigyan Gaurav Das from Vellore Institute of Technology, Vellore, and this was my first GIAN program. It was a very new exposure and experience for me since it's my first program itself of my career, and I would like to thank Dr. Pankaj Kalita, Sir Christophe, and the organizing team for giving me this wonderful experience and exposure. Thank you very much.
Any other participants would like to say something? Madam, maybe you can say from because you came from far.
Good evening. Myself, Damanjeet. I am of Kalita in Punjab University, Chandigarh. So I came for this course just to explore what is going on in the solar side. I am from the electrical side. So when I came here, I came to know that solar collector is playing major role than PV itself. So this is very beautifully designed and well organized course. So I am thankful to Dr. Deepak Kalita and Professor Ménézo for this wonderful work. In addition to this, the thing which I like the most, diversification of participants. This course is eye-opening for UG, PG, PhD, postdoc and faculty also. So this is the most, you can say, tempting thing which I can appreciate. Okay, this is a mixed group. Likely we go for FDPs, there only faculty. Here UG, PG and all type of students are there. So their energy, their enthusiasm, it clearly indicates that they are very much interested in these type of upcoming and going on areas. Thank you.
Thank you very much, madam. So any other participants who registered online would like to give some comment? Would like to give or would like to say something? Yes, yes.
Good evening, one and all present here. So myself, this one where I joined this course through online. I'm currently studying in Assam Engineering College in Department of Electrical. So it was a very great experience. I wanted to join this course offline, but due to some of my problems, I couldn't. I apart from online and that
Yes, continue.
Yes, Leon, please go ahead.
Yeah, it's great to be part of such a great event. It's my first event that I have joined under GIAN course. I'm very grateful to both of the faculties and those who have organized such a great event. And I hope that I could be part of such a great event, upcoming great event. Thank you.
So thank you very much for your nice comments. Yeah.
Good evening, everyone. I am Kritika Patwari. I am a research scholar at NIT Meghalaya. So, all three of us are from NIT Meghalaya, and we are working on solar collection device only. So, anytime we are stuck anywhere in any problem, we always switch to YouTube for Pankaj sir's videos, and whenever he visits our college for any lectures or any events, we are always present to listen to him, to learn from him. So we are all time we are a great fan, and we always follow your ideas on this area. So this time when we got to know that that GIAN course is being organized on the solar collector technologies, so we opted that anyhow we will visit, we will attend the lectures and everything. And Professor Christophe sir, so we are very much grateful to you for everything, and we have learned a lot, and it was a great experience. And Pankaj sir, like from before also, we are thankful to you, and now, and we further expect to visit your institute or any such opportunities. We are always there for. Thank you, sir.
It's a very nice experience. So this time what happens, we have visited IIT Bombay, and then I met one assistant professor. He joined in one of the NITs, I forgot where, Hamirpur, I think. And then he said he has attended my thermal classes in MOOCs, and then he scored well and he got the job. And only he has prepared based on my things. And then he came like different way, and then said, he just hugged me, like, no, because of me, he got this opportunity. So if we get to know this kind of things, it is very, very satisfying. So thank you very much for your comments, and then maybe next time we'll see some other content so that this will be helpful for other people as well. So thank you for coming, and really I would like to thank our team, especially Pushpendra, Dr. Pushpendra Singh. He helped me a lot. Because one round of applause to him, because see, the way he works is different than others. I don't know, he's different man. Because see, we have done it and he has designed so nicely so that instantly we'll get all the marks and then we'll grade everything. So now all the things are ready, but I cannot disclose because of some administrative reason. And then not only this, and all the activities he has nicely executed. And thanks, Pushpendra, for your nice help, and then for working for a good reason. Okay, and of course, I'd like to thank each one of you for coming from far and taking participations in this event, and hope these informations will be useful for as your humanity, and then maybe your respective individuals. So thank you very much. I also like to share a few words.
I've said these words for my for my last tutorials, that I was very happy to exchange with you and to have interaction. It was very pleasant to have also some questions from you, some remarks, and I feel that you were quite concentrate. So it's very nice to make a speech and to see that the audience is concentrated and is follow. And so no, it was a very rich experience too. And yes, I hope that all the things that you have seen, because it was a lot of information, have been of interest for you, and maybe some parts are more interesting than the others, but I think it was quite complete with both of our presentation. So thank you very much.
And I also see the similar collaborations with the professor, and then we can continue the collaborations in terms of research, in terms of student exchange, or maybe similar kind of activities in future. So thank you very much, Professor Christophe, for coming here to Assam and then giving your knowledge to big audience of the country. So thank you very much once again. Yeah. Yeah. So thank you. Now we'll distribute certificates. Also, I actually missed to acknowledge CET people like Kaushik. He helped me a lot. From the time of submission to get all the approvals, and then designing those posters. Really, he helped us a lot. Of course, as a whole CET team. Without their help, this type of program, it is impossible. See, from day one, from at 9:15, everyone is involved till this Friday, the last hours. So without their help, this kind of program could not have been possible. So I'd like to thank from my heart to everyone of CET. Thank you so much for your help. Yeah. You can distribute one by one. Randomly you can do it. It's not
Sir,
we'll distribute you.
Abhigyan Gaurav Das, Miss Ankita Basak, Miss Ankita Basak, Dr. Ankita Gaur, next, Bipasmita, Mr. J. Venkatesh, Miss Kritika Patwari, should be Doctor na Adam, Mebratu Adam, Kritika, Mebratu Adamu, Mr. Mriduparna Bunia, Mr. Mriduparna, Mr. Nirvan Kalita, Mr. Ravindra, This is Alag Ravindra. Dr. Sanjana Talukdar. Dr. Sanjana Talukdar. Dr. Sayaram Bosumatari. Mr. Siddhartha Kumar Gohai. Dr. Shyam. Mr. Deepak Agarwal. Dr. Hakim Nias. Mr. Hankrai Basumotari. Mr. Hemontojit Medhi. Dr. Madan Kumar Srinivasan. Madan Kumar Srinivasan. Dr. Damanjit Kaur. Mr. Ashish B. Khelkar. Ashish B. Khelkar. Mr. Omang Klekhraj. अपने लोगों को भी दिए. Mr. Akash Dilip Kamble. Mr. Mrinmoy Sharma. Ms. Priyanka Dwara. You didn't receive, na? I'll call your name. Okay. Dr. Pushpendra. Mr. Robindra Kongshabanik. Mr. Shubham Nath Laskar. Next is me myself. Next is me only. Manas Jyoti Das. Urvashi. Vikas. Dr. Vikas Kumar Thakur. Mr. Biraj Das. Vikas Kumar Thakur. Mr. Bituban Das. हो गया आपका मेरा भी यहीं पे था. I hope everyone present have received their certificates. Your name please. Mr. Piyush Yadav. Sorry, I missed you out. Anyone else who has not received the certificates? Thank you, sir. Over to you.
Okay, so with this, we'd like to conclude our GIAN program. So once again, I'd like to thank everyone. So thank you all, and maybe we can ask for a group photo one more time. Oh, just one event is left. Yeah. Just a minute. So it's a small moment for you. Yes. Yeah, this is special.
सर को कौन देगा सर आप दे दीजिए I would also request आप देंगे I would also request Dr. Pushpendra to felicitate the coordinator of this whole program, Dr. Pankaj Kalita.
Now I think everyone is here. So who will design now how to stand? Miraj will design.
Now you, sir and Christophe sir both stand on the front. Let the participants stand at the back.
Online participants, can you please turn on your camera so that we can take a photograph? Yeah, very good. Very good. Rupreha, are you there?
প্লাষ্টিকৰ চুকি ভনিয়াটো ল'বা লৈ কিনে মাৰিবা